you'll find that there's two different poles. I've written north and south on these ones. They don't normally come like that. If you put the north and the south together, they stick. But if you put the north and north or south and south together, they repel. They repel. See, they don't want to go together at all. And you can force them together if you want, but if you do, they will spring away the second you let them go. But when magnets repel each other, I find that some of the most interesting stuff. Check this out. This is just a small container, and I've got a magnet in here, and I have a loonie attached to it so that it fits nicely in the container like that. For the top, I've attached two magnets together, and I have another coin on it. And if you put them in there, I've made sure that the two poles repel each other, which means this magnet will just sit there and float. Magnetic levitation. Very interesting. And you can pop the top on that if you want and just carry around a levitating magnet. Now, there's a couple fancier ways you can levitate stuff with magnets. This is just a wooden frame I've made. This is completely not necessary. You can use just about anything in your house. A desk lamp works really well. The important part is I've tied a magnet to the end of this arm here, and this is a bolt, which is attracted to the magnet, but it's got a thread tied to it, so it can't get there. Just far enough that it will actually hang in mid-air. Look at that. It's not attached to anything. It's just being pulled up by the attraction from the magnet. The thing is, as soon as you pull the bolt away far enough, it will lose the attraction and it'll just fall. Very cool. Here's one that's a little bit more complicated, but is also really neat. This one uses disc magnets, which have a circle or a hole in the middle of them here. And you put two around a pencil and then four more in such a position that you can put the pencil against this wood on the side and it will just levitate on its own. You can even give it a spin. Look at that. And if you want to make the levitating pencil yourself, there's step-by-step instructions on how to build an easy-peasy version on our website. Meantime, we are gonna max this out. Magnetic levitation on Science Max Experiments at Large. But you're probably thinking, what are we going to levitate? Well, we're going to levitate meat. At least, that's the plan. That's why I'm going to the Center for Skills Development and Training. Come on.
Okay, who turned out the lights? Ow, what was that? Why is this room so small? And only going down to waist level. This is the weirdest room I've ever been in. Where am I? What's going on?
Hey, Matt.
Hi, Phil.
This is Matt. He's from JobMaster Magnets. Now, you guys use lots of big magnets, right?
That's right, we do.
Awesome. So maybe you could help me max out this.
Wow. You did a great job of building the levitating pencil experiment.
Yeah, so what's going on here exactly?
Well, all magnets have at least a north and a south pole.
Right.
And when you put like poles together, they want to repel.
Oh, okay. So have you ever levitated a person?
Not yet.
Well, let's do it.
All right.
Do you think we can use these?
We can try.
Okay, well, put that one on the ground. And, okay, so north, and I'll put the north one on my foot here. And then if I just step, oh, wait a minute. If I step, stop moving. If I step on that, step on the, okay, well, first of all, this magnet keeps sort of moving away from me when I try to push down on it. What do we do? How do we fix this?
Well, we need to keep the magnets in position so that they don't move around when you try to bring them together.
Yeah, because I have to come straight down on it, don't I?
That's right.
So why don't we attach this one to the floor?
Good idea.
And then we'll put a board on this one, and we'll see how it goes.
Perfect.
Okay, let's do it.
All right.
This is a magnet. This is a magnet. This is a magnet. This is a shoe. What's the difference? To know that, you have to know your magnets. This is a donut. It does not stick to this magnet. This is a spoon. It sticks to this magnet. These paper clips stick to this magnet. This shoe does not. So what is attracted to magnets? only things that are ferromagnetic. Here's the difference. Horseshoe, horseshoe magnet. This one is a magnet. This one is not. But the horseshoe sticks to the horseshoe magnet because this one's a magnet and this one is ferromagnetic. Only things that are ferromagnetic are attracted to magnets. Things that are not attracted to magnets, they're not ferromagnetic. Plastic, banana, mitten, sandwich, magazine. No, but how do you know? Do you go around the world sticking a magnet to every single thing one at a time? Hey, Ma, I need you to come over. I need to see if you're ferromagnetic. No, ferromagnetic. No, you don't need to do that. First of all, only metals are ferromagnetic. So that eliminates all your clothing, your luncheon meats, your magazines, what have you. Everything that's non-metal, you don't need to worry about. Never mind, Ma, it doesn't matter. But this clock is metal. It doesn't stick. Well, not all metals are ferromagnetic. Mainly just the ones with iron, nickel, or cobalt. And there you have it. Now you know your magnets. I hit the phone on the magnet there. Okay, can you hear me, Ma? Hang up the phone. Hang up the phone, Ma. My first attempt at levitating had the magnet sliding all over. So the plan is to take the bottom magnet and attach it to a big wooden board so it won't go anywhere. Then attach another plank to the top magnet to make it a little easier to stand on. Okay, that is definitely attached to the floor. Thank you. All right, now, if I just get this lined up, oh, look at that. It could totally, oh, wait a minute. Totally, it doesn't want to stay put. Oh, wait a minute. They levitate. Come on. Levitate. Why doesn't it want to stay? It just doesn't. Should I stand on it? Okay, I'll stand on it. Here we go. And am I levitating?
No.
No. So why isn't this working?
Well, just like your pencil experiment, we need a shaft through the center to hold the magnets in position.
Oh yeah, maybe we could use like a ring magnet.
Yes.
That like we used with the pencil.
Right.
And
we're gonna need stronger magnets.
we're gonna need stronger magnets. Are the ring magnets strong?
Yes, they can be.
Awesome. All right, let's do it.
All right.
Now it's time for a Science Max quiz. Which one of these things do we have magnetism to thank for? Birds flying south in the winter, music, or a sandwich? If you picked A, you're right. Some birds migrate in the spring and fall using the Earth's magnetic field. Many animals can sense the Earth's magnetic field and use it to navigate. Migrating birds fly hundreds or thousands of kilometers north or south when they migrate in the spring and fall. A compass works the same way, by using magnetism to point to the Earth's magnetic North Pole. But if you picked B, music, you're right! Here's some music. The way you're hearing this music is because the musicians recorded their instruments using microphones, which use magnets. And then the signal was translated by a computer and stored on its hard drive, which uses magnets. Then it was broadcast to your TV and comes out your speakers, which use, you guessed it, magnets. And for those of you who said you have magnetism to thank for your sandwich, well, you're right. You see, you'd probably go to the kitchen to make that sandwich, right? Well, I'm guessing you got all of the tasty ingredients from your refrigerator? Well, it works on electricity, which is produced by magnets. And then there's an electric motor in the fridge that circulates the air and keeps it cool. And guess what? Magnets. And finally, the door on your fridge stays closed because the door has magnets. So there you go. You can thank magnetism for birds flying south, music, and your sandwich. It just goes to show, when you're talking about magnets, everybody wins because magnets are everywhere. This has been a Science Max quiz.
Here's an experiment you can do with a bag of water. Take a sharpened pencil and carefully push it through the bag. If you do it carefully, it won't spill. The reason this works is because the bag is made of polymers, long stretchy chains of molecules, and also because the pressure of the water against the pencil prevents any water from spilling out. Now, we're gonna max it out. This is a very large bag of water, and here I have some very large pencils. You ready? Oh. That's one. That's two. Here we go. Should I go from the bottom? Ta-da! Science! Okay. I know what you want. Like I was saying, science!
Turns out trying to balance two repelling magnets on top of each other is pretty much impossible. Here's why. This is a magnet, and here is the magnetic field. It's often drawn with lines like this, but actually the magnetic field radiates out in all directions. Really, think of the magnetic field kind of like a ball. When you try to balance another magnet on top of the first magnet, it's about as hard as balancing one ball on top of another ball. So here's the plan. Just like the levitating pencil, we're going to use ring magnets because we can put a shaft through the center of one ring, then drop another ring magnet on the shaft. It will keep them perfectly aligned. Then it's just a matter of putting the bottom magnet on a board to keep it stable and using another board so I can stand on it, and ta-da! Magnetic levitation! Or at least that's the plan.
Okay. Board.
Magnets.
Magnets. Ooh, look at that. Awesome. And now I'm gonna put the platform on. Nice. I got some weights here. Let's see how this works. Yeah. This is gonna work amazing. All right, think I should try it?
Give it a try.
Okay. Here we go. Yeah! I'm doing it! I'm levitating! What?
Just a little bit.
Oh, really?
Yeah.
So, yeah, what do we do?
We need more power.
More power? I like that idea. How do we give it more power?
More shafts, more magnets.
Okay, sure. Well, why don't we do 1, 2, 3, 4 shafts, and then we'll have magnets on all the shafts.
Great idea.
All right. Let's do it. If you attach something ferromagnetic like this washer to a magnet, not only does it stick, but the magnetic field travels down the metal, making it a magnet too, which means you can stick more and more things to each other, and they will continue to stick until you run out of magnetic field. You can do this yourself at home with anything ferromagnetic. Paper clips work pretty well, or washers like I have, or screws or bolts, and they'll continue to stick to each other as long as the magnetic field is strong enough. You can see it's getting pretty weak here, and they'll all stay magnetized as long as the first one is still attached to the magnet. But if you want to go even further, all you need to do is keep adding more magnets to reinforce the magnetic field. I've got a few here like this. Let's get the chain started like that. And then I've got a magnet attached to this washer, so it will keep the magnetic field strong. And I continue to add one magnet, one washer, and we'll just see how far I can go. You you can even sculpt it a little bit. Look at that. And then at the end, a whole bunch of paper clips. Eventually, the weight will make it fall off, but it's a lot of fun to play with magnets and make art. Speaking of art you can make with magnets, you can also make sculptures. When everything sticks to everything else, you can make some pretty fancy designs. This is a rare earth magnet, a very strong one, and a bunch of nuts that I've gotten. And this one here is an electromagnet, but electromagnets are a little different because they need an electric current to work. Check this out. This is sort of a magnet dude with crazy hair. There's an earth magnet here, and this is a giant screw, and these are some metal bits, and then I've got 2 more magnets at the top here to hold on his crazy wire hair. He's got crazy wire hair because he's crazy magnet dude. Now, of course, we couldn't just talk about magnetic sculptures without maxing it out, so let's max it out. This is a bunch of scrap metal from leftover experiments, and I've got a bunch of rare earth magnets, and now I'm gonna max out a magnet sculpture. Let's see. There you go, a maxed out magnet, me! I made this guy out of metal pipes with earth magnets in between, and these are his arms attached, of course, with magnets. His hand, his little metal pieces attached with magnet. Steel wool for the hair, and of course, hat, non-magnetic. All right, here we go. Ready? Want to see a magic trick? Simple copper tube. Drop things through it. Nothing unusual happens, but watch when I drop a magnet through. What? It's not magic, it's science. Because the magnet creates a magnetic field, when it goes through the tube, the magnetic field repels the magnet upwards. Now, the field isn't perfect, so the magnet doesn't come to a stop, but still, it slows down from a fall to a nice, graceful drop. Take a look from above. Pretty amazing, right? Magnets. Not magic, science. So I've managed to levitate on some magnets, but just barely. What Matt and I needed was more power. So instead of having one shaft and one pair of ring magnets, we're going to use a larger board and put a shaft on each corner. Then we'll have 4 times the power because we're using 4 times the magnets. Hopefully this will be strong enough to get me floating on a cushion of magnetic energy. And magnets?
Magnets.
Okay, here we go. This is gonna work great. And top board. Ooh, what do you think?
Looks great.
Yeah. Okay, here we go. Matt?
You're levitating.
I'm levitating! Woohoo! All right. It feels cool. It sort of feels like surfing a little bit. All right, thank you so much, Matt. That was amazing. And there you have it. Science Max, experiments at large, magnetic levitation. You know, I'm surprised we could do an entire episode on magnets, and we never actually got them so close to the camera that the camera went all weird, because cameras and magnets, they don't, oh dear. No, that's okay. I can fix this. If I just maybe, no. Maybe if I put the magnet to the camera again, that would, okay, that's not, that didn't help. Oh, okay, well, thanks very much for watching Science Max, Experiments at Large, and we'll see you again as soon as we get into the camera. Today, we're gonna be looking at the power of magnets. 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 Wait, okay. This one here is called a neodymium magnet, or a rare earth magnet. It sticks to this magnet. Magnet. Ramona, the fish fell. Have you ever done a science experiment and wondered what it'd be like if you did it big? I have. Yeah!
My name is Phil, and I take your everyday science experiments and do them big. This is Science Max, Experiments at Large.
Science Max!
Today on Science Max, we're looking at
Chemicals!
Chemicals make up everything around us, and we're finding out which ones you can mix together to make spectacular science.
Woo! Cutest science ever.
Today on Science Max, Experiments at Large.
Greetings, Science Maximites! My name is Phil McCordick, and the name of the show is Science Max Experiments at Large. Today, we're taking a closer look at chemistry. Ooh. Chemistry is the science of atoms and molecules, the things that make up all matter, and how they interact with each other. Take, for example, this glow stick. Actually, don't take it, because I kind of need it. The glow stick doesn't glow until you... The glow stick doesn't glow until you break the barrier and mix the two chemicals, and they start to glow. Huh? Pretty cool, huh? Chemistry. Now, the chemical reaction we're looking at today is the old vinegar and baking soda volcano. But this reaction doesn't have anything to do with volcanoes. It's chemistry. Now, this experiment is totally safe, but I do recommend you get an adult's permission before you do it because it's very messy. Yeah. First, you're gonna want baking soda and vinegar. These are your two main ingredients, but you'll also want dish soap and red food coloring if you want it to look a little bit more like lava. Now, I like to mix the baking soda, red food coloring, and dish soap together with a little warm water, so all you have to do is add the vinegar. And when you do, this is what happens. And there you go, chemical reaction. Now, I know what you're thinking. You're thinking, Phil, how much vinegar or baking soda do I use? Well, I'm not gonna tell you. This is where you can be Science Maximites. Try different amounts. More vinegar, more baking soda, more dish soap. Who knows? Write down the amounts each time you use it and find out what amounts work best. That's called science. And that's what we're gonna be looking at today, chemistry in all its forms. And of course, because it is Science Max, Experiments at Large, we're going to max out the vinegar and baking soda volcano. So I'm off to the Center for Skills Development and Training. Come on. Hey, Talina.
Hi, Phil.
How you doing?
Good, how are you?
Good. This is Talina. She's going for her PhD in chemistry from McMaster, right?
Yep.
Awesome, which means you can help me max out the baking soda and vinegar. We need vinegar. You grab that vinegar. And vinegar volcano. So what happens when we mix these two chemicals?
Well, vinegar is an acid and baking soda is a base, and when you mix them, they neutralize each other to produce carbon dioxide and water as a byproduct.
So acids and bases are kind of like opposites.
Yep.
So I guess that makes sense. When you put them together, crazy stuff happens.
Yeah.
Awesome, chemistry. Okay, so I want to use this much vinegar and this much baking soda.
What's with the fish tank?
The fish tank is where I want to mix it all together. What do you think?
Awesome.
Maxed out. Okay, let's move the fish tank somewhere where we won't make a huge mess. It's a little heavy with all that. We gotta. No, we're gonna have to take a couple trips. That's kind of heavy. Okay, so we'll take this and that, and then this, and that. No, hold on. I can do it. Just one more. Okay, good. Okay, good. Yeah. I took too much. Uh-oh. That's good, Ramona. Put it in the background. Put the sign in the background. Yeah, in the BG. I love the BG. Chemicals. What are chemicals? Are they things you have in a lab in a jar that say chemical on them? Well, yes, but if that's all you think chemicals are, then you need to know your chemicals. Turns out the stuff in the jar is a chemical, but the jar itself also made of chemicals. The table I'm putting it on, made of chemicals. My lunch, chemicals. Roller skate, chemicals. My jacket, chemicals. This guitar, chemicals. My shoe, chemicals. This watch, chemicals. This fish, chemicals. 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 Me, chemicals. You, chemicals. Ramona, chemicals. No, I said your chemicals. Never mind.
This is it. The periodic table of the elements. All matter in the universe is made up of these pure elements. They go together in different ways to make up everything. All matter.
Think of it like building blocks. These little atoms are some of the elements on this periodic table. You got 1 oxygen, 2 hydrogen, bam, you got a water molecule. 1 carbon, 2 oxygen, hey, it's carbon dioxide. 2 carbon, 2 oxygen, 4 hydrogen, skadoosh, vinegar. 1 sodium, 1 chlorine, hey, that's salt. All matter in the universe is just the stuff on here combining into these. And now, you know your chemicals. Sugar.
Let's take a closer look at what's going on when we mix vinegar and baking soda. All chemicals are made of atoms. There's only 4 types in our reaction: carbon, oxygen, hydrogen, and sodium. When they go together like this is a molecule of vinegar, or acetic acid. And this is a molecule of baking soda, or sodium bicarbonate. When chemicals react, they switch atoms. That one goes there, this one goes over here, and then this one turns into this, and then what you end up with are new molecules. This one is called sodium acetate, and this one is carbon dioxide gas, the gas you breathe out. And do you recognize this one? Right, water, H2O. Why all this happens gets complicated, but the study of chemistry is all about how molecules are built and react with other molecules.
All right, Talina, you ready?
Yep.
You're gonna pour all your baking soda in the fish tank, and I'm gonna pour the vinegar into this bucket, because you don't wanna pour them together right away. Okay, you ready?
Yep.
Okay, go for it. When you're doing your PhD in chemistry, do you get to do stuff like this?
Yeah.
Really?
Got to do a lot of fun reactions in the lab.
Oh, I'm jealous. Have you ever done this much vinegar and baking soda in one time?
I can't say I ever have.
There you go. That's what I like to hear. I already put the soap in the bucket so it would mix with the vinegar when I poured it in. Are you done your baking soda already?
I am.
I'll pour faster. Oh, faster.
It smells vinegary.
It smells vinegar. It makes me want French fries. Okay, Talina, you take this very full bucket of vinegar and dish soap.
Thank you.
I will take this one. Uh-oh, we still have our 3rd bucket. Okay, I'll do these both at the same time. Okay, ready? On the count of 3. 1, 2, 3. Whoa! 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 Wow.
Okay.
That's awesome. So the one thing it didn't do, it didn't shoot up in the air though.
Yeah, it's because the top is quite open, so you would need to constrict it to get it to shoot up.
Oh yeah, because we're using just sort of a square, a rectangular prism container. We should get something that's maybe something more like our vinegar bottle, right? Because
Yeah.
there's lots of space down here, but then it forces it into a tighter opening at the top there, like a volcano.
Yep.
And what else can we do to make it even more powerful, to max it out?
Vinegar is only 5% acid, the rest is water, so you could try using 100%.
So what kind of acid is vinegar?
It's acetic acid.
So vinegar is actually only 5% acetic acid
Yep.
and 95% water. So you can get 100% acetic acid?
Yeah.
Can you get 100% acetic acid?
Yes.
Awesome. Why don't we get a container that's sort of shaped like a funnel, like a volcano,
Yeah.
and 100% acetic acid, and we'll do it again.
Sounds good.
All right, let's do it.
Our vinegar and baking soda reaction went pretty well. But now we're gonna try it with a much stronger type of the same kind of acid you find in vinegar.
Carefully putting this down. And watch out for the baking soda. You never know when it'll get out. And, well, I guess that's just baking soda, huh?
Yeah, that's pretty safe.
Yeah, okay, good. So this is baking soda vinegar volcano version 2. We have this differently shaped glass. What do you call this again?
That's an Erlenmeyer flask.
Why is it called that?
It's actually named after a scientist.
Did he look like that? Was he sort of shaped like this?
No.
No? Was he just a good chemist?
Good scientist, and I think he designed the glass.
Oh, see, there you go. So if you want to have a glass named after you, be a good chemist and design a glass. I want to make a fill beaker. So this is 100% acetic acid.
Yep.
And what's the difference between this and vinegar?
Vinegar has 5% of this and 95% water. But this is 100%, so it's much stronger.
Much stronger. Can you put this on your French fries?
No, I wouldn't be putting it on your French fries.
No? As chemicals go, how dangerous is this?
It's not too dangerous, but you definitely don't want to be breathing it in, and you don't want to be eating it.
Or getting it on your skin. That's why I'm wearing these fancy gloves. So what I'm gonna do is I'm gonna pour the acetic acid in this. What's this called?
That is a graduated cylinder.
Because it finished school. So it graduated. Now you're gonna mix water and food coloring and soap all together.
Yep.
And pour it into there?
It'll help dissolve some of the baking soda, so hopefully it'll react better with the acid.
Sounds good. Face protection.
Oh.
All right, that's good. And now, when we do it, I want to add the funnel at the end to like accentuate the concentration of, but I don't know if it's gonna go so fast that I won't be able to get it in there, but we'll try it.
Try it.
Vinegar baking soda volcano version 2. Woo!
Good thing you got the mask.
It smells a lot like vinegar. It's really strong.
Oh.
That was pretty good. But what can we do to make it even bigger?
Well, you could try using a different chemical reaction.
Ooh, okay. Like what?
The decomposition of hydrogen peroxide produces oxygen gas, and so that one's pretty vigorous if you use a catalyst.
So we want something that makes a lot of gas so that it makes a lot of bubbles when you put the soap in it.
Yep.
Great, let's do it. And the sooner we leave that smell, the better, I think, for my taste. Today we're combining two different chemicals to create a reaction. Sometimes chemicals can combine in a way that makes them very different from how they started out. For example, this is sodium, or Na on the periodic table. Now, the sodium tablets are in mineral oil because sodium reacts very strongly with water, even the water in the air, or especially the water in my skin. Watch what happens when I drop a sodium tablet into this beaker of water. Very cool and very dangerous.
And this is chlorine, or Cl on the periodic table. Chlorine gas is very poisonous. So,
So, what happens if we combine these two deadly substances? Do we create some sort of super poison? Something more deadly than anything else known to science that causes fear and chaos in chemistry labs all over the land? No, we create salt. Good old normal table salt. These two substances combine to make NaCl, salt. Something completely and totally safe. Chemistry.
We've gone from vinegar and baking soda to 100% acetic acid in baking soda, and now we're doing the
Vinegar and baking soda volcano version 3. No longer vinegar and baking soda.
Nope.
What are we using this time?
So here we have some hydrogen peroxide.
Oh, that's the stuff you use at home to put on a cut, right?
Yeah, but the stuff at home's only 3%. This one's 30.
So much stronger,
Much-
10 times stronger.
Yes.
And is this more dangerous?
It's definitely corrosive, so wear your gloves.
Corrosive means it could eat your skin,
It can burn your skin a little
which is
bit.
why we are wearing gloves and blast shields. What's gonna mix with this?
So here we have some potassium iodide, which is a salt, and it's mixed in with some water.
The most important part of this reaction is the fact that it creates gas,
Oxygen
which
gas?
makes bubbles when you put in dish soap, right?
Yep.
So one big squirt of dish soap like that. Mix it up. Now we go over to the blast zone.
That's plenty.
All right. Now that's a reaction. Looks like there's steam coming off here. Why is that happening?
Well, it is an exothermic reaction, so heat is being generated as the reaction proceeds.
Oh, cool. Can we lift our visors now?
Yep.
Awesome. And what's being released? What's the gas that's coming off here?
So it's oxygen gas that's being produced.
Oxygen. What we want to do is make this even bigger, but first, can we do it again?
Sure.
Because I have an idea. Hold on. I think we should repurpose our old volcano. What do you think?
Sounds like a good idea.
Okay, so if we put it over here. All right, volcano version 3.5. Hydrogen peroxide, potassium iodide. Right, here we go. Whoa!
Looks like lava.
Whoa! Look at that. Now that is a big volcano eruption.
Just covered the town.
That is completely, yes. That town is gonna be very clean because it's all soap bubbles. It's the cleanest volcano this side of Science Maxville. So I still think we can do this bigger, though, right?
I agree.
Oh, I know. What if we use some sort of a tube, like maybe one of these, right? And then we attach it to like an air compressor.
I think you'd get some height.
Yeah, and we go outside.
The atom in 60 seconds.
The atom is the smallest unit in a chemical element. Atoms are made of 3 parts. Part number 1 are these guys, protons. They have a positive charge. The number of protons determines the element. 1 is hydrogen, 2 is helium, 3 is lithium, and so on. The protons sit in the middle here, which is called the nucleus. They sit in here with part number 2, these guys. They're neutrons and they have a neutral charge. Now I've got 8 protons and 8 neutrons in this nucleus, making this an atom of oxygen. Orbiting around the nucleus are these tiny guys. They're electrons and they have a negative charge. I will demonstrate using kittens.
Kittens are perfect because just like electrons, kittens are really small. And just like electrons, kittens move around randomly. You never know where they're going to be, but an oxygen atom should have 8 kittens, or electrons, somewhere inside. These kittens are constantly escaping, but guess what? That happens with electrons too.
There you go, the atom, a nucleus of protons and neutrons surrounded by randomly moving electrons. Cutest science ever. How do you guys feel? Did you learn something? Huh? Pause up. Who learned something?
Talina and I have made a bunch of chemical reactions, but in our quest to max things out, we've got a new plan. Hydrogen peroxide and potassium iodide create gas. One way to max out the reaction is to contain the gas in something like a tube. We're gonna put the hydrogen peroxide in the tube first. Then we're gonna put in the potassium iodide in the top through a one-way valve. Then we're gonna pressurize the container. When it finally reacts, it will shoot up through the valve and we'll see how high we can get our stream of bubbles to go. But be warned, capping anything and not letting it escape is never a good idea. So we've got a release valve to make sure things work out. This is one of those experiments that's definitely on the list of don't try this at home.
Vinegar baking soda volcano version 4, hydrogen peroxide, potassium iodide. And what we're gonna do this time is we're gonna put it in this tube. Hydrogen peroxide goes in here. And we've got, Talina, do you have the potassium iodide in syringes?
Yeah, 2 syringes full.
2 syringes full. About there is good. And then soap. Good amount of soap in there. And so what we're gonna do is we're gonna close this off and tighten it up. And then we're gonna pressurize the whole system. And then we're gonna add the potassium iodide. And it's going to be spectacular, we hope. Okay, that's on tight. This is all good. Putting this down here. And potassium iodide goes in here.
Ready?
Hoods down. Ready? 1, 2, 3, go. And we back away slowly. Whoa! Whoa! Yeah, that's what I'm talking about. Okay, let's check it out. Woo! All right, there you go. Vinegar and baking soda volcano maxed out. Thank you, Talita. That was great. If you guys want any instructions for the stuff that we've done today, they're all on the website. And thank you very much for watching Science Max Experiments at Large. We kind of need to clean up a lot, don't we?
Yeah.
We have out here, we have the other room. So tell you what, you get a mop, I will get the hose and a wheelbarrow for the suds.
Science Max is a show where we take small experiments and do them big. If you want to try these experiments yourself, go to our website for instructions. But not all the experiments on Science Max are the kind you should try at home. This one, yes. This, no. Try this, don't try this. A big yes, a big no. I don't know how you could possibly do this one at home. And remember, if you're ever not sure, ask an adult. Thanks for watching Science Max Experiments at Large.
Chemicals! Chemicals!
The chemistry of hydrophobic coating literally repels water molecules and doesn't let her.
Chemicals! Chemicals!
Hydrophobic coating.
Bleh. Chemicals! Yeah.
2 carbon, 2 oxygen, 4 hydrogen.
Have you ever done a science experiment and wondered what it'd be like if you did it big? I have.
Yeah!
My name is Phil, and I take your everyday science experiments and do them big. This is Science Max Experiments at Large.
Science Max!
Put on your helmets for this episode of Science Max. We try to build a human-sized cart powered by inertia, plus Newton's laws from a caveman to crockery. Inertia on Science Max Experiments at Large.
Greetings, race fans and science maximites. I am Phil McCordick, and this is Science Max Experiments at Large. Today, we're going to be experimenting with the drag racer. Huh? Pretty cool. It works like this. You pull the string and get the wheels going really fast, and then you let it go, and it just drives away on its own. The interesting thing is I don't have to push it, it goes by itself. It all has to do with Newton's first law of motion, which is an object at rest tends to stay at rest, and an object in motion tends to stay in motion. Yeah. Let's get building. Here is everything you need to build your very own dragster. You need some popsicle sticks, some straws, and some shish kebab skewers. I love these. You can get these at the grocery store. Let's see, some elastics, and of course you want wheels, and I just cut my wheels out of cardboard.
So here's a quick explanation of how to build your dragster. First, use anything round to trace 3 circles out on your piece of cardboard. Remember, you want 2 big and 1 small circle. Then, cut out your wheels. Then it's time to make the frame of the dragster using popsicle sticks and elastics. Just put 2 popsicle sticks together, then wrap the elastic band around them to keep them together. First you build one side, then the other side. Then, add some pieces across the middle to give it support. Remember not to put any popsicle sticks too near the ends because they'll get in the way of your wheels. Next, cut the straws into small pieces and use an elastic band to tie them to the ends of the popsicle sticks. Then it's just a matter of sticking the shish kebab skewer in a wheel, passing it through the straws, and sticking on the other wheel. Don't forget that the small wheel goes in the middle at the front. You can trim the skewers afterward by just breaking it off short.
If you want step-by-step directions on exactly how to do this, you can go to our website. It's all right there. Now the last part is wrap some string around the back axle so you can pull and the wheels will spin. let's check it out and see how it works. Didn't work that well, did it? That's because we haven't added the secret ingredient. Plasticine, the perfect secret ingredient for all of your dragster needs. And also sculpting, because that's what it's for. Remember how I said an object at rest tends to stay at rest, and an object in motion tends to stay in motion? Well, the heavier something is, the more force you need to change its direction, either get it moving or make it stop. That is called inertia. It's the tendency for an object to resist a change in motion, either getting it going or making it stop. So, the heavier we make the wheels of our dragster, the more they will resist a change in motion. So what I've done is I've stretched out my plasticine, and then you roll the wheels of the dragster around in the plasticine, and this will make each wheel way heavier than just the cardboard by itself. And it will make it much better in terms of keeping the dragster going, because if the wheel has more weight, it will have more inertia. Now, I have to wrap the string around the back axle, just like that, and there we go. All right, let's try it out. All right, let's give it a shot and see how it works. Pull on the string, get the wheels going real fast, and there it goes. Now, of course, this is Science Max Experiments at Large, and we are going to do it again, and we're going to do it much, much bigger. That's why I'm going to the Center for Skills Development and Training. I thought it was bigger. Oh, right. Hey, Chris.
Hey, Phil.
How you doing? Chris is from Logix Academy, and he is going to help me max out our dragster. Now, you guys at Logix Academy go into schools and build all kinds of cool stuff with the students, right?
That's absolutely right. This is our dragster over here, actually. And this one has an electric motor, which is kind of fun. And these gears touch.
Ooh.
Wheels get going.
I like that.
And...
Oh, all right. See, our dragster works on good old human power. You pull the string, and there it goes. Now, you have a physics degree, right?
I do.
Which means you know Newton's first law of motion.
Of course, an object at rest tends to stay at rest.
And an object in motion tends to stay in motion. I thought it was gonna come from over there. Yeah, come on. All right, Chris, I want to make a dragster big enough that we can ride.
Whoa, okay. Well, it's gonna have to be pretty big.
Yeah, I think we have enough wood, though, right?
Yeah,
And
looks like
oh, look, I've got some wheels.
Perfect.
These are bike tires, and I filled them full of air, so they're bouncy. Check
Excellent.
it out. Oh, it's okay.
So, yeah, we build our frame out of wood,
Yeah,
attach the tires on, and then find a way to get them spinning.
and if the tires are spinning,
Yeah.
we don't actually have to push the cart because it'll just go on its own?
That's the idea. The inertia should carry, in the wheels, should carry us down the track.
So in this case, the object in motion is the wheels.
That's right.
And it wants to stay in motion, which means that when it hits the ground, it'll push the cart.
And hopefully us too.
And hopefully us too. All right, let's get building.
Let's do it.
So Chris and I get to work building the dragster. Our maxed out version is gonna look just like the popsicle stick version. A triangular frame with 2 large wheels at the back and a small one at the front. What's more, we're gonna do the same thing to get the wheels spinning. We're gonna attach a rope and give it a pull. When we drop it down, the inertia of the wheels should make the dragster take off.
All right, here we have our dragster. This is nice, Chris.
Yeah, it looks good.
So the only thing I don't understand is what are these for?
Right, so these are gonna help us lift the wheels off the ground, like this.
Oh, okay.
Pull it back, and what's gonna happen is we're gonna run real fast with that string, and we're gonna give it a little kick, and hopefully it'll take off.
Ah, all right, I like it. So I just run backwards as fast as I can.
Fast as you can.
All right, here we go. Ready?
Yep, ready?
Okay, safety glasses on. And, oh, wait, did you want to sit on it, or?
Oh, right. Let's wait until we see it working, and then we can...
Okay, dry run.
Okay, try one.
Ready?
Go! Run, Phil.
And go! Yeah!
So here's what happened. Remember, the cart has no power of its own. It was able to drive away from a stop using the inertia it got from its spinning wheels, and a little bit from Chris's kick.
That worked pretty well.
That was awesome.
Yeah.
I think we can make it go even better.
You think so?
I just think we need a bit more speed.
Yeah. All right, well, let's pull it back to the start.
Okay.
So what, the wheels weren't going fast enough?
Yeah, I think so. I think that you running, was great, but maybe if we use something motorized.
Well, I think using a motor feels like cheating.
No, not on the wheels. Maybe,
Oh, just to get the wheels spinning fast?
Yes, that's right.
But I don't know how that would work.
Well, I was thinking a power drill.
A power drill?
Yeah.
I don't get it.
Okay.
How do we use a drill?
Let me explain. So we'll take a drill.
Right.
And we'll attach it right under this axle here. And that'll get the wheel spinning a lot faster than we had it before.
Oh, I see. So you put the drill right here at the end, and
That's right.
it'll spin the wheel.
That's right.
Huh.
That's the idea anyway. And once we get it up to speed, hopefully a lot faster than before, give it a kick, it should go a lot farther.
Okay, great. So that's way better than me running all the way back with the rope.
I think so.
All right. Now here's the real question. Should we just go for it and have someone ride it when we do it with the drill?
Well, who gets to ride it?
Oh, rock, paper, scissors. Okay.
Let's go.
1, 2, 3. Oh,
Yes.
All right. I will get a drill.
Okay.
What kind of bit do we need?
Hex bit.
Here's a fun experiment you can try. If you have something heavy, like this glass of water, and you put it on a piece of paper, you can experiment with inertia. If you move the paper slowly, the glass moves with the paper, because the friction between the paper and the glass is enough to overcome the inertia of the glass. But if you move the paper quickly, the friction is not enough to overcome the inertia, and the glass stays put. And now, let's max it out. Okay, let's do it. All right, now you might be tempted to try this at home, and you can, but please, for me, promise that you'll let an adult know you're about to do this. And don't use breakable plates. Use plastic plates, because this will take a couple times of practicing before you get it right. Put something on the plastic plates, because the heavier they are, the better it will work. All right. Did I mention not to do this at home unless an adult knows you're doing it? I cannot stress that enough. Okay, deal? All right, deal. Here we go. And there you go. Newton's first law. Thank you.
Our dragster worked pretty well, but now we're gonna try sitting on it and seeing if the inertia of the wheels is enough to accelerate the dragster and the human rider. Because we're gonna need a lot more inertia, we're gonna make the wheels spin even faster using a drill.
All right, power tools! Yeah, power tools! Woo! Yeah! Sorry.
When I attach the drill to the wheel, it works really well.
Yeah, that is really gonna work. All right, let's do it for real. So, what do you want? Helmet or blast shield?
Blast shield.
Blast shield. All right, there you go. You ready?
Go. There you go. Whoa, man.
Okay.
Remember, the faster the wheels are spinning, the more inertia they will have.
Ready? Ready. And. Well,
What happened?
so you went a foot. 1 foot. So why didn't that work nearly as well as the last time we did it?
Well, I think my extra weight caused a bit of the problem.
Yeah.
So the inertia wasn't able to carry us forward.
But the whole point of this is so that someone can ride the dragster. Because why build it if we can't ride it?
That's exactly right. I think if we're gonna have someone ride it, we need heavier wheels.
Well, on the small one we use plasticine.
Yeah.
I don't know if that's what we should use.
What if we used car tires?
Car tires. Oh, what, on this?
No, I think we're gonna have to build something bigger.
So so we build a whole new frame.
Yep.
What if we got like the axle of the back axle of a car or something?
It's a great
The
idea.
back axle of a car, and then what we use the drill
I don't think the drill's gonna be enough.
to move the. Why? You don't think it's gonna be enough to move the back axle of a car?
Yeah, it's too big.
So what do we do?
Well, what's good at moving The back axle of a car.
Well, I mean a car, but we would have to take it off the car, so.
We could use another car.
We could use another, we could use another car.
You could use another car.
You'll have to explain how that works.
Okay.
Let's go get the stuff, and you can tell me how we're gonna use. So how do we use another car to make the first car go?
Okay, I'm thinking we jack one car up,
Yeah.
back our big dragster.
Newton's laws in 60 seconds.
Isaac Newton was a super genius, and among the many things he did was come up with 3 laws of motion that describe how everything moves or doesn't move. I will demonstrate using myself. Newton's first law: an object at rest tends to stay at rest. An object in motion tends to stay in motion. Newton's third law is for every action, there is an equal and opposite reaction. These sandbags weigh as much as I do. So when I push them forward, I go backward the same distance. Now, Newton's second law is F equals ma. Force equals mass times acceleration. How hard you push something is equal to its mass or its weight times its acceleration or how much you change its speed. I know, that one's a little bit more complicated, so we're gonna have a whole other segment describing that one coming up. Meantime, let's recap. Newton's first law: object at rest tends to stay at rest, object in motion tends to stay in motion. Newton's third law: for every action there's an equal and opposite reaction. Newton's second, Newton's 3 laws of motion. Now how do I get down? How do I get, oh wait, I know. Oh no, that was not a good idea. That was...
Now it's time for Science So Simple, a caveman could do it. This is a caveman. This is a door. It is a well-known scientific fact that cavemen do not know how to open doors. This is Newton's second law. Force equals mass times acceleration. Our caveman thinks he can open the door if he uses force. Well, what if he was to walk briskly into the door? Then the force that he will hit the door with will be equal to his mass, or how much he weighs, times his acceleration, which will be walking speed to 0. It didn't work, did it? No. Looks like we need more force. If we want to increase the force, we need to increase the mass, increase the acceleration, or both. A rock! That's perfect. If the caveman holds the rock, he has a greater mass. Now we just need to increase the acceleration, which means going faster. Let's try running. Go on. A little further. That's good. Now the caveman is going to run at the door. To get more force, we've increased the mass to a caveman plus a rock. And we've increased the acceleration to go from running speed to 0. And there you have it. That's how Newton's second law works. Join us next time for how doorknobs work. Our inertia-powered dragster just wasn't maxed out enough. So Chris and I built a second dragster, the Dragster Mark II. This one is a welded metal frame, and instead of bike tires, we're using car tires because they're much heavier than bike tires. And to get the tires spinning fast enough, we're going to use a car. That's right. We jack up an actual car and have the tires touch each other. Then we can get those heavy tires spinning fast enough to get enough inertia to get me going from nothing. The Science Max build team pulled out all the stops on this one. Just like the smaller version, the dragster has to be up on jacks so the wheels don't touch the ground as they get spun up. The wheels of the dragster touch the wheels of this working car, which is also jacked up. That's how we're gonna get them spinning fast enough.
Chris is over there. He's got a rope, just like I'm gonna have a rope. And when we're ready, we're going to run forward and pull it off the jacks, and our dragster will go. We hope, right? That's the plan, right?
Yep.
All right.
I think it's gonna work.
I think we should do it. Ready, Chris?
Ready.
You ready, Paul?
Ready.
Fire it up. Go, go, go. Faster, faster, faster.
Keep
Faster,
going.
faster.
Keep going.
All right, Chris. After 3, right? 1, 2, 3, go. Nice.
It's pretty good.
Yeah, that worked. All right, are we ready for me to be in it?
I think so.
All right, we're gonna do it. The helmet's in the Max van. Do you have the keys for the Max van? Keys for the Max van. Here's another small experiment you can do with inertia. Take a stack of checkers or game pieces like I have here. Oh, or coins. Coins work really well. And a ruler or something else that's flat. This is the kind of stick they give you at the hardware store to stir your paint with. Now you can knock checkers out of the middle of the stack without the stack falling over if you're very careful. You see, the friction of the checkers leaving the middle of the stack won't be enough to overcome the inertia of the rest of the checkers. Ready? Now, let's max it out. Oh, I have these pizza boxes, and they should work the same way. You see, you get a stack, and don't worry, I've already eaten all the pizza. And I put them on there like that, and now I need a ruler. And what I've got is this cricket bat. You see, it's got a nice flat edge, just like the ruler. Now, if this works right, I can hit it hard enough to knock out just 1 or 2 pizza boxes, and the rest of the stack should stay. Here we go, ready? Science! Awesome. And there you have it, Newton's first law. An object at rest tends to stay at rest, and an object in motion tends to stay in motion. An object in motion tends to stay in motion. Usually there's a sign that kind of...
Well, our inertia-powered dragster worked really well. And now it's time for the final step. Me, riding it to glory!
Now, I know it probably doesn't need saying, but don't try this at home. Not that I think you really can try this at home because this is kind of involved, but I figured I should probably tell you guys just in case you were tempted to try it at home. We know what we're doing. We know what we're doing, right, Chris?
Yes.
Yes, yes, we know what we're doing. All right.
Fire it up. Keep it going. Keep it going. All the way.
Whoa.
All the way. 3, 2, 1, go!
Yeah! Yeah!
Woo! How's that for inertia?
Wow, look at that. That's amazing.
Cool.
High fives! Yeah!
Let's recap. The weight of the tires, as well as how fast they were going, provided enough inertia to accelerate me and the weight of the dragster. The objects in motion, the wheels, wanted to stay in motion so much they moved the dragster all by themselves. Inertia, and Newton's first law of motion.
Thank you for joining us on Science Max. Let's go again. Your turn?
Yeah, my turn.
Okay. Woo. Inertia! Whoa. Science! Whoa!
Action!
I can't do it. Whoa!
Have you ever done a science experiment and wondered what it'd be like if you did it big? I have.
Yeah!
My name is Phil, and I take your everyday science experiments and do them big. This is Science Max, experiments at large.
Science Max!
This episode of Science Max is a messy one. We're looking at solids, liquids, and gases, and things in between, like cornstarch mud. Today on Science Max, experiments at large.
Behold the power of states of matter! Greetings, Science Maximites! I'm Phil McCordick. I think I overdid it with the fog machine. This is Science Max, Experiments at Large. Can you even see me? Let's go over here. Today we're talking about states of matter. Now there are three main states of matter. Solid, like this table, liquid, like the water in this beaker, and gas. Yes, thank you. And we're also going to be looking at the things that kind of go in between. Things that are sometimes solid, sometimes liquid, like cornstarch mud, which is very easy to make. All you need is water and cornstarch, which you can get at the grocery store. Mix it up however much you want. Just remember, 2 parts cornstarch to 1 part water. Twice as much of this than you have of that. Very easy. Mix it up and you get cornstarch mud, which sort of seems like a liquid unless you hit it. And then it becomes solid. But if I pour it, it's a liquid. Even if I hold it in my hand and I hit it really fast, it turns into a ball, and it will stay in a ball as long as I keep hitting it or squeezing it. But as soon as I stop, it turns into a liquid again. Now we're gonna max this out. We'll go through the portal and learn more about solids, liquids, and gases. Yeah, right. That's why I'm going to the Center for Skills Development and Training. And, oh, no, wait, that's the code for the fog machine. Wait, stop. Stop, it seems to be stuck. Oh, never mind. I'll fix it later. Right. Hey, Judy, how are you?
Hi, Phil, how are you?
Good. Judy is going for her PhD in chemistry, right?
Yes.
Fantastic, because that means you can explain cornstarch mud to me. Now, is this a solid or is it a liquid?
Well, it kind of has properties of both. It's called a non-Newtonian fluid, so that makes it a liquid.
A liquid? Well, I mean, it pours like a liquid, but when you hit it, it's a solid. So why does it turn solid when you hit it?
So when you're pouring it, the particles are still far apart, so they can't interact with each other, and so they stay a liquid. But when you're hitting it, you're jamming the particles together, and they line up to become a solid.
Now, does it still work the same way if we have a lot more of it?
It should.
Great, because I've got this 20-kilogram bag of cornstarch, and I have 34 more of them.
Wow, that's a lot. But I think you'll need a much bigger container.
Much bigger container, great. I got some wood over there. Why don't you go, and I'll follow you.
All right.
I'll follow you. I'm coming. Yeah, thanks, Ramona. And give me one of them fizzy drinks. Not too fizzy, just sort of medium fizzy. Thanks a lot. Hello, do you have trouble knowing what is a solid, liquid, or gas? Are you confused by Jell-O? I mean, which is it? Is it a solid or is it a liquid? Water is a liquid, but what about when it's ice? Well, you gotta know your states of matter. There are 3 main states of matter: solid, liquid, and gas. And there are 3 rules that you need to figure out which one of them is which. Does it flow? Does it fit the shape of its container? And can you squeeze it? Rule number 1, does it flow? Solid, liquid, gas. Here's a gas. Does it flow? Do the particles pour over each other and cascade down? Yeah, they do. Does a liquid flow? Yeah, it does. Does a solid? Nope. Rule number 2, what happens when you put it in a container? Does it take the shape of the container? Gases take the shape of the container. Liquids takes the shape of the container. Solids do not take the shape of their container. I know what you're thinking. You're thinking, I get the whole pouring and taking the shape of the container, but come on. Liquids and gases, they do both of those things. Well, it all comes down to rule number 3. Can you squeeze it? Now, solids, you can't really squeeze them. Liquids, you can't really squeeze them. Gases, bam, you can squeeze them. You see, gases compress. Liquids and solids, they don't really compress very well. The other difference between gases and liquids is gases will take the shape and the volume of the container they're put in. Liquids don't do that. So there you go. Solid, liquid, gas. And the rules. Does it flow? Does it take the shape of the container? And can you squeeze it? Now you know your states of matter. That'll be $6.50. Cash only.
So, what is cornstarch mud and how does it work? Well, cornstarch mud is a non-Newtonian fluid, which means it behaves differently than you, or Newton, would expect. Here's cornstarch, and here's water. Cornstarch is made up of large, blocky molecules like this. Water is made up of much smaller, rounder molecules like this. When you put them together, it looks something like this. It all has to do with how the molecules slide past each other. When you put light pressure or slow pressure on the mud, the water molecules and cornstarch molecules have time to shift out of the way. But when you put a sudden pressure on it, the water molecules squirt out of the way, but the cornstarch molecules don't have enough time. So you get a section that's nearly all cornstarch, which acts as a solid. Cornstarch mud is a shear thickening fluid. Shear is talking about the force of things sliding around, in this case, the molecules. So when the shear force is strong, the fluid thickens. Shear thickening. So here's the plan. If Judy and I make enough cornstarch mud, could we run across it? Let's find out.
Yeah, I think mine is just the right consistency. How's yours, Judy?
I think I'm ready too. This is much harder than I thought.
Yeah, it's really hard to get it mixed at the very beginning, but mine is ready to go. Okay, here we go. First batch. You ready?
Yep.
Dump it in. Woo! Woo! I thought that would be more.
I thought so too.
It's really not filling this up very much, is it?
No.
Huh, that's a lot of cornstarch. This is great, but I think we're gonna have to go a little faster than this.
I think we need some sort of mixing device.
Yeah, I mean, we don't have to do this by hand. We can get some sort of machine to help us.
Yeah.
Right on, high five.
Oh.
We shouldn't high five when we have this stuff on our hands.
Nope.
Yeah, good call. This science is delicious. This is rock candy. It's basically crystallized sugar, and you make it by turning a solid into a liquid and then back to a solid again. Here's how you can make it at home. You need a container that you're not gonna need for a while, and some water, some sugar. You can use brown or white. I like to use brown. And an adult. Here's why you need an adult. You want to dissolve 3 cups of sugar into every cup of water. And you can't do that unless you heat the water. So get an adult, a saucepan, and heat the water up, pour the sugar in, and keep stirring until it's all dissolved. Then pour it in your container and let it cool down. Then you'll need a shish kebab skewer, which is something you can get at the grocery store. Cut it down to the right size so it fits nicely into your container. And then dunk it in your sugar and get some crystals coated around the stick. These are seed crystals, and they get the whole process started. And now you have to wait for these to dry, otherwise they'll just fall off the stick when you put it in the water. So I've got one here that has dried out. You'll also want something to keep it from falling in the top of the container, so I'm gonna use a clothespin. Put it in there and dunk it in the container like that. And now for the final step, if you want, you can add food coloring. I like to use red because it reminds me of science. And I'm gonna use the stick to actually stir that up a little bit. There we go. Now, the dissolved sugar crystals in the water will slowly grow on the crystals that are already attached to the stick, and it will eventually grow into a rock candy pop. But it takes about a week. No, I'm just kidding. I've already got one that's standing by. Here we go. This one has been growing for about 7 days. And there you go, rock candy. Delicious science. Now, how can we make this any better? I mean, it's crystallized sugar. It doesn't get any more maxed out than that, does it? Yeah, it does. Come on. This is a giant container of sugar water, and I've been brewing a massive rock candy crystal in it for a while, but it's sort of getting a little bit too big to fit out the top of the container, so you know what? I'm just gonna put that back in there and chalk that one up to science because, well, eating a rock candy crystal that big would definitely not be good for my teeth, so, yeah.
So our big experiment is to take a whole lot of cornstarch and fill a trough to see if we can run on it. But mixing it by hand was going to take forever. So Judy and I got a drill with a mixing attachment on the end.
Whoa, sorry. All right, so Judy, I'm noticing a bit of a problem here.
What is it?
Well, if I mix at the top, everything's fine, but as soon as I get it a little bit deeper, and then it gets really tough, and the whole bucket starts to spin, and the drill stops.
Yeah, I think it's because the drill's trying to mix it too fast. When we're mixing it by hand, it's slow and you can still let it stay a liquid, but now you're just making it solid.
Right, because it's a sheer thickening fluid, so if
Exactly.
you hit it really quickly with something, like the blades of this spinning really quickly in the thing, it'll suddenly turn into a solid, and it'll be really hard to mix.
Yep.
So we go slow. Going slow. Going slow. Suddenly realizing that if we go slow, we'll be here forever.
Yep.
You know what I think we need? Whoa, sorry. You know what I think we need? We need a different way to mix this.
Yep.
We need a way to mix more of it, and we need a way that it doesn't hit it with blades that suddenly go through it really quickly.
Something that can mix on a large scale, but slowly.
I have just the thing. Come with me.
All right.
The interesting thing about bubbles is they're a gas surrounded by a liquid. So get some dish soap and some water, and then be science maximites and find things around the house that you can make bubbles out of. Just about anything that has holes will do. Or, or I like this one. I call it the loud bubble. Or now it's time to max it out. I'm here at the Ontario Science Center, and this is Anthony. Hey, Anthony.
Hey, how's it going?
Good. So you are amazing at bubbles.
I am. I've been practicing for a while. Let's get started.
Okay.
You're gonna make an okie dokie sign like this.
Uh-huh.
You're gonna dip it right into our bubble solution. Come on, get right in
Okay,
there,
right
right in
in.
there. Make sure you get it all. Oh, that's a little too much.
Well,
That's
then I
good.
can make two.
And then you're gonna keep that okie dokie sign. You're gonna blow very gently.
Nice.
I brought these two giant sticks here, and I don't know if you noticed, but I've got a smoke machine here.
Right.
So we'll turn that on, and then if you press that green button there, you're gonna shoot some smoke, and we're gonna try to catch that smoke in a giant bubble. You ready? Okay, and I'm gonna try to... Oh, that was so close.
great.
Did you see that one? You give it a shot. Nice! Oh, check that out! That's amazing! That was huge. Try it again. Let's see if I can get the smoke machine. Here we go. Go for it, go for it. Push right towards. Oh, check that out! You did it! Look at that! Look at that! No! Smoke, and it bounces on the floor because the floor, it doesn't have any oils like our hands do. Isn't that amazing?
That was
oh my
great.
God, that was so cool.
That was great. You know what I think we should do?
What's that?
Giant bubble, tons of smoke.
Done.
Okay, here we go.
Let's do it. You ready?
Giant bubble, tons of smoke. Go.
Awesome! Oh my God! Look at that! Amazing! Look at that! That's crazy!
Maxed out bubble. Well, there you go. Giant smoke-filled bubbles.
Awesome!
Yeah.
Judy and I tried mixing the cornstarch mud using a drill with a mixer attachment, but it didn't work. We should have known better. Here's the mixer in our cornstarch mud. Usually, a mixer works by going really fast and mixing everything together. But remember that cornstarch mud is a sheer thickening fluid. So, when the blades of the mixer tried to go fast through the cornstarch mud, it did what it always does, turn solid. The faster and harder you try to move it, the more solid it will become. This means the only way to mix it would be if we made the drill go very, very slow, which wouldn't speed things up at all. So with the drill another lost cause, Judy and I need the biggest thing around that could mix stuff
Come
up.
on back. Good. Little bit more. Perfect. A cement truck is a perfect thing to mix because all we have to do is get all the cornstarch up in here and it'll mix it, and it doesn't move it too fast. It goes nice and slow, so hopefully a shear thickening fluid will be fine. I'm gonna get Judy. She's driving the truck. Hey, Judy, that's perfect.
The only problem is we needed to get all of those bags of cornstarch into the hopper of the cement truck.
I didn't think it'd be this messy.
We needed to call the entire Science Max build team to help us out.
This is possibly the messiest thing I've ever done. Awesome! Woo. Hey, Judy, you wanna lift up any bags?
I'm okay, thanks.
That's okay. I'm having a lot of fun, so I can do them.
Cool.
Oh no! Oh no! Oh no! Yeah! I got most of it. All right, I think we're done. I think that's enough bags. Let's start the mixing! So, what do you think, Judy? Do you think it's gonna work?
I think so, because you're mixing at a very large volume, but at a very low speed.
Yep.
So throughout the process, it'll stay a liquid until we're ready to run across it.
That sounds exactly like the kind of science I like to see. You know what I really like is that every time I move, more cornstarch comes off. It's like I'm a human fog machine. This is liquid nitrogen. Nitrogen makes up most of the air we breathe, but if you get it really, really cold, it turns into a liquid. The fun thing is you can use it to make other things really, really cold too, like this banana. I have frozen this banana solid thanks to the liquid nitrogen, and normally a mushy banana would not be able to hammer in a nail, but whoa, because it's frozen, I can hammer this nail into this block of wood. So that got me wondering, if I can turn a banana into a hammer using liquid nitrogen, could I turn a pumpkin into a sledgehammer? Let's find out. Pumpkin sledgehammer, take one. No, I think the answer is no. You cannot turn a pumpkin into a sledgehammer with liquid nitrogen. All you can do is make a really, really big mess. I'm gonna have to clean this up, aren't I?
Now we have a cement truck to help us do the mixing for our cornstarch mud. After making a giant mess getting the cornstarch into the cement truck, it's time to see if it worked.
Hey, Phil, how's it going?
Yeah, it looks like it's mixing pretty well. I'm really glad we're not doing this by hand, because it'd take a really long time. We've almost got it at the right consistency, but it's taken some time. But it's getting a little dark out, Judy. I don't know, do you want to quit and go home?
No.
Of course not. That's not what we do in science. Oh, here we go. Yeah!
Awesome.
All right, let's see it. Let's see if it's... I like how it comes down in little steps. And look, it's working just like it should. I hit it, and it's solid, but you can see it's pouring like a liquid. Yeah, here comes a big wave.
Wow.
Here it comes. Oh! Wow!
And it's totally filling up.
Oh yeah, filling up really fast. I think we should stop pouring very soon.
Yep, we may not have a big enough trough. Yep.
Liking it.
It's good.
Yeah. I think it's time. It's not even done pouring, but I'm gonna try it. Okay, you ready? Whoa.
Oh, and you did it!
Whoa. You can't. You have to get back onto the sides before you stop moving.
Or else it becomes a liquid.
All right, it's your turn.
Okay.
Here.
Go.
Okay, ready?
Okay.
You gotta hit your feet really fast.
All right.
Okay, go.
This actually works.
Because cornstarch mud is a sheer thickening fluid, it means it stays a liquid until you hit it suddenly, like with your hands, or in this case, our feet. And then it turns to a solid. So as long as Judy and I keep slapping our feet down with enough force, we can walk on top of it.
One more dance.
All right.
And
let's
tell you
do
what,
it.
we'll do one more dance.
All right, let's do that.
Okay, ready?
All right.
And go. All right.
All right.
There you go.
We've done it.
Solids, liquid, gases. Thanks very much for joining us on Science Max Experiments at Large. Woo! Hey, Judy, catch. I have to be careful because the banana will shatter if I'm not careful. I think it's stuck on the bottom. I call this one the loud bubble. Oh, well. I call this one the loud bubble. I don't think I can do it. Have you ever done a science experiment and wondered what it'd be like if you did it big? I have. Yeah! My name is Phil, and I take your everyday science experiments and do them big. This is Science Max, Experiments at Large. Science Max! Science!
Today's Science Max is all about balance.
Okay.
If it's a potato or if it's me, figuring out how things balance is what we're all about.
It works really well!
Swinging, spinning, and staying put. Today on Science Max Experiments at Large.
Greetings, Science Maximites. Today, we're gonna be talking about, balance, or what you call balance in science, which is center of gravity. Now, the center of gravity is a place you can find in any object where it's equally balanced on all sides. I balanced this spoon on the eraser of this pencil, and where the spoon is balancing is its center of gravity. But if I take this little tiny dime and put it in the spoon, it doesn't balance anymore. But if I put the dime in this spoon and balance it in a different spot, I can find the new center of gravity, and the spoon balances again. Here's another experiment you can do. Take a potato and a ruler or a stick. Try to balance the potato on the ruler. I'm gonna save us both a lot of time. It's really hard to do. The potato does have a center of gravity, but because of its shape, it's going to be really hard to find and really hard to balance. But if you take some forks and you stick them into the potato, you're no longer just trying to balance the potato, you have to balance the forks and the potato. And it gives it a very different center of gravity, which makes it a little bit easier to find and a little bit easier to balance. Ha-ha!
Whoa! Let's take a closer look at how the center of gravity works. Using our potato. No, that's too close. Back off a little bit. Okay, good. If you want to find where the center of gravity is, you can hang an object and draw a line straight down. Then hang it from a different spot and draw another line. Do this 1 or 2 more times and you can see where the lines meet is the center of gravity. If our potato was balanced on a stick, the center of gravity is a long way from the stick, so it's going to be pretty hard to balance. Now, let's stick some forks in the potato and try again. One line there, a line there, and a line there, and you can see that the lines all come together down here. That's right, the center of gravity doesn't have to be on the object. With the center of gravity way down there, when we try to balance the potato and the forks on the stick, you can see the center of gravity is much closer to the stick. That makes it way easier to balance.
Now, because you're Science Maximites, I'm sure you know that a potato and forks is just the beginning. Everything you have in your house has a center of gravity, which means, theoretically, you can balance anything. Try it yourself. Find things around the house and see if you can get them to balance. And if you can't, try adding things to increase the center of gravity and make it a little bit easier. Now we're gonna max it out. That's why I'm gonna go to the Center for Skills Development and Training, and we're gonna explore center of gravity even more. See if we can get something to balance. And what better thing to balance than me? Oh, table, right. Hey, this is Sandhya and Swapna. No, Sandhya and Swapna.
Right.
And they are going for their PhDs in science. And you guys, thank you for coming.
Thank you.
Work with Let's Talk Science, right?
That's right.
All about science education, just like us. And I'm glad you guys are here because I need to max out this. Oh, look at it balance. Whoa. Hey, whoa. Okay, I got it, it's fine.
Good. So we're gonna get a gigantic potato?
No, I thought we would use me instead.
So you're the potato.
Yeah, I guess I'm the potato. All right. And I need something to balance on.
Well, how about a tightrope?
Oh, yeah, a tightrope. Have either of you done a tightrope before?
Nope.
Me neither. All right, let's set one up.
All right.
Okay, good. Yeah, you're right.
We're gonna take our balancing potato experiment and max it out. To get a potato to balance is pretty hard, but if you stick forks in the potato, it works a lot better. In our maxed out version, we're gonna balance on a slack line, which is sort of like a tightrope. It's a flat strap tightened between 2 points. And in this version, I'm the potato. And instead of sticking giant forks in me, which is not something I want to try, Sandhya, Swapna, and I are going to experiment to see what I can do to improve my balance.
There. We're using this ratchet strap above a crash mat because we only have it about 3 feet off the ground, but it's still gonna be really hard to balance on, right?
Right.
Okay, so who gets to go first? Okay, here we go. Ready? Hey.
Got it?
No. Okay.
I think what you need to do is spread your mass out more to be able to find that center of gravity easier.
So I should balance on one leg?
Start by trying to put your arms out. Let's
Good
try
call.
this again.
Trying it again. All right.
All right, arms out.
Okay.
Let's see if this works.
Okay, so when I say, you're gonna let go. Ready?
All right.
1, 2, 3, go. No!
It's a little bit better.
It was a little bit better.
A little longer.
That I went from 1 second to 3 seconds. Yeah!
Yes.
I would like to actually take one step.
Okay.
That would be nice.
Well,
What else can we do?
maybe we can try weights. Try and hold them out.
If I have weights in my hands, that would increase the center of gravity in terms of putting
Putting it
the
out.
weight on the outside. You guys have something we can use?
Sure, yeah. Actually.
Okay, good. Wow, these are heavy. Okay.
These are weights.
Yes, they are. Well, that's what they're for. They're supposed to be heavy. Good call. When I hold this one, and I'll borrow your shoulder, Swapna, and then when I say, Sandhya, pass me the other weight. Here we go. Ready? And pass me the weight. Oh, no. Okay, that didn't work. Okay, good. Whoa. Okay, let go. Okay, let go. Oh, no. Oh, it's really hard. I feel I would work better if I could lift the
Yeah.
weights up, but they're too heavy for that.
All right.
So what else can we do?
Well, tightrope walkers use a long pole so that they can balance on a tightrope.
That's right, I've seen that. Do we have a pole?
I think go find one.
Okay, great. I'll put the weights away. Have you ever heard someone say, I will be back in a jiffy? Well, now you can tell them that's almost impossible. You see, a jiffy is an actual measure of time. It's 1/100th of a second. You see this timer? The first number is seconds. The second number is tenths of a second. And that third number that you can't even read, it's going so fast, that's hundredths of a second. Each one of those is a jiffy. Here are some things that happen in a jiffy. A cheetah moving top speed travels 20 centimeters. A hummingbird flaps its wings almost once. Can you blink in a jiffy? Nope, takes 10 jiffies for that. How about snapping your fingers? 8 jiffies. So the next time someone tells you, I'll be back in a jiffy, you can tell them it took 170 jiffies just to say that.
So I tried walking the slack line, and I wasn't very good at it. Holding my arms out at my sides seemed to help a little. Then I tried holding some weights to see if that would make any difference, and the weights were so heavy, I couldn't really hold them out very far. Now the plan is to try a long pole. Tightrope walkers use long poles to help them balance. The longer the pole is, the more it affects your center of gravity, especially because you can move it up and down to help you stay balanced.
Ta-da!
Nice. So the important thing on this is what? The balance, right?
Yeah, you
That's
want to
right.
find the center of gravity of that as well.
So
you
try
can
and find the center of the
balance
pole.
it.
The center is right there. That's where it balances.
There, you got it.
Okay. How do I hold this and get up on the strap?
I'll help
You're
you.
gonna help me? Okay. Oh. Okay. Uh-huh. Whoa. Whoa.
You good?
Okay. I think I got it.
Okay.
Yeah. Whoa.
You're balancing.
Check it out. Hey, this isn't so bad.
Hey, look at that.
You can really use it to help correct when you start to fall. You just move the pole, and that's whoa. Totally helping my center of gravity stay right in the center above the strap. Whoa. Whoa.
You can do it.
A long pole can help tightrope walkers and me balance in two ways. First, it lowers my center of gravity. Normally, a person's center of gravity is about here. But with a pole, it changes to way down here, much lower to the thing I'm walking on. But a long pole also helps in another way, because in order to fall off the rope, I have to rotate. It's easier to rotate something that has mass in the middle than it is when the mass is spread out. That's why you put your arms out when you want to balance. A pole works just like your arms. The mass gets spread out way more, and it makes it much harder to rotate around the rope and fall off.
There you go. Center of gravity. We're done. Usually we don't have it figured out this quickly. Usually we struggle a little bit more. All right, high fives.
Way
we did
to
it.
go.
Way
Awesome.
to go. So we did it.
Yeah.
We achieved what we set out to do, balanced with a pole. So how else can we use science to make my balance better?
Well, tops are great because when they're spinning, they balance.
That's right. So the forces used when something spins is something I can use.
Yeah.
All right, this calls for another small experiment. Are you guys good here?
Yeah, sure. We'll keep practicing.
Awesome. All right, back to the lab.
Bye, Phil.
Here's another experiment that's all about balance. Take a pencil and try to balance it on its tip. Doesn't work that well, does it? But if you take a pencil and stick it through a circle of cardboard and try it again, it works. The reason is because this circle is spinning, it creates a force that keeps the pencil standing up. As long as the circle is spinning fast enough, it counteracts the force of gravity because of the conservation of angular momentum. The conservation of angular momentum. The conservation of angular momentum.
Science Max presents Ways to Sound Super Smart. A top will balance when it's spinning. It works because it spins. But why say it that way when you can impress your friends and all the adults you know by saying conservation of angular momentum? Why does a top spin? Because of the conservation of angular momentum. Between you and me, we know that it boils down to the fact that it's spinning. But conservation of angular momentum is how you say it if you're studying physics in university. Just remember to thank Science Max when you impress everyone by telling them a top balances because of, say it with me, the conservation of angular momentum.
Now, let's max this out. Gyroscopic force is pretty amazing. Because this bike tire is spinning, it's hard for me to move it. But it's really hard to see how much it resists a change in orientation unless I do this. Ha ha ha! It looks like it's defying gravity. But really, it's because the amount of force needed to change its orientation is more than the force of gravity pulling down on it. It won't last forever, only as long as the bike tire keeps spinning. But you got to admit, it's pretty cool science.
And whoa! Science! Look at that, it totally balances.
Yeah.
So this is a great way to balance. Do you think it'll work if I hold it?
Well, let's see you try.
All right.
right.
So I'm going to use you to get up on the thing, and Cindy, you go give her. Yeah, that's good. And spinning it up. Here we go.
Ready?
Yep.
Okay.
Yeah. Whoa. You can feel it. I can really feel it resisting, and
Yeah.
I think it would work.
I think it just needs to be spinning a lot faster.
That would make even stronger, yeah. It kind of hit my chest, so.
You know what? Maybe you should keep it out to one side.
Well, it's still spinning, yeah.
Well, won't that?
I think you need two.
Oh yeah, you're right, one on either side. It'd be great if we could actually have some way I can keep my arms free though.
Yeah.
Oh, I know. Get two wheels and we rope them into some sort of backpack situation.
What?
And we have a way for you guys to get the wheels spinning really fast.
I don't know.
No, I have it all in my head. Trust me, come on, I'll show you. Wait, you guys go around. Come, don't go on that side of the. Time for a mini-max. Here's how you can use the forces of things spinning around to defy gravity. Well, sort of. Take a ping pong ball and put it in a plastic container like a cup, or this is the top of a CD spindle. Put it in and start spinning it around. If you do it right, you can get the ball spinning only on the sides of your container and not touching the bottom. That's centripetal force at work. Oh. It works a lot better and is much more impressive if you have something that doesn't have a bottom. Fortunately, I do. This bucket doesn't have a bottom. Put the ping pong ball in the bucket and spin it around, and if I'm very careful, I can lift the bucket into the air and ta-da! I'm defying the force of gravity. Science! Now I know what you're thinking. You're thinking, Phil, is that it? Is that all you're gonna do? No, of course not. This is Science Max Experiments at Large. This is a garbage can with no bottom in it. And this is a bag of golf balls. Let's see what happens when we put them together. Well, I managed to keep one golf ball in my garbage can. But as you can see, it works really well. And there you go, sort of maxed out. This is a garbage can with the bottom cut out, and this is a soccer ball. I'm gonna see if I can keep the soccer ball inside the garbage can using centripetal force. Okay. It's working! It's very tiring though. How do you throw out a garbage can that's been used? Science! Here's a fun experiment you can do that plays with the forces created when you spin something. Get a flat platform or a tray and tie rope to every corner. Get an adult to help you with this. Then you get a cup of water. Use a plastic cup, definitely, just in case. You put it on the tray and you start spinning. Now the force is created when you spin something. Centripetal force pulls the water to the outside of the circle. And because the centripetal force is stronger than the force of gravity, no water spills out of the cup, even when it's upside down. You slow it down very carefully, you'll see that all the water is still in your cup. Now, I definitely suggest you do this experiment outside, and I definitely suggest you do it with an adult. because when you get tired, which you will, if you don't stop it carefully, you'll have to explain what you've been doing. Science!
Using science to improve my balance has totally worked so far. So now, Sandia, Swapna, and I are trying to figure out how to use the forces created when a wheel spins to help me balance. We need a spinning wheel on one side and one on the other. I've decided to take 2 bikes and remove the handlebars, seats, and front wheels, then cross them over each other and attach them to a backpack. Sandy and Swapna can use the pedals to spin the tires fast, and I will use the gyroscopic force to balance. Or at least, that's the plan.
Behold, the gyroscopic stabilization backpack! Stabilization away! I'm excited. Okay, you think it's gonna work?
I think so. I'm kind of skeptical.
Really? You're skeptical? Why?
I don't know. I don't know if you can do it.
I don't know if I can do it either, but that's why we do science!
Let's see it.
Okay, spin me up. Okay. Oh,
Ready?
yeah.
All right.
And, oh, ready? Go.
Yep.
Oh, yeah. It's working.
Cool.
It's working.
It's actually working.
It's good. Oh, what's getting harder? It's getting harder.
Uh-oh.
Oh, that worked really well until the wheels stopped spinning.
Yeah.
And then what happened?
Well, when the wheel was spinning, it was resisting motion in all directions so that you wouldn't fall.
Yeah, but when they stopped spinning,
You didn't have that anymore.
that doesn't do anything. It's just a 50-pound weight on my back.
Yeah. Exactly.
Right. So I guess that's why tightrope walkers don't use spinning wheels. They use a pole instead.
Right.
But we've proven that they can.
Exactly.
Yeah. Max out, high five.
Yeah.
Woohoo! Yeah! I now have the balance of a ninja circus performer thanks to
Science.
Thanks for watching Science Max Experiments at Large. Okay, spin me up. Spin me up. And we'll do some more science. Gyroscopic backpack to the rescue. All right, let's go.
Science Max is a show where we take small experiments and do them big. If you want to try these experiments yourself, go to our website for instructions. But not all the experiments on Science Max are the kind you should try at home. This one, yes. This, no. Try this, don't try this. A big yes, a big no. I don't know how you could possibly do this one at home. And remember, if you're ever not sure, ask an adult. Thanks for watching Science Max Experiments at Large.
We should put fans on them and I can fly.
Now, I know what you're thinking. You're thinking, why didn't that work? And the reason is because I didn't do it right.
I got 2 turntables and no microphone.
I am defying. Come back here, spin it around, and spin it around, spin it around, and spin it.
Have you ever done a science experiment and wondered what it'd be like if you did it big? I have.
Yeah!
My name is Phil, and I take your everyday science experiments and do them big. This is Science Max, Experiments at Large.
Science Max!
Newton's third law is the science behind balloon-powered rocket cars. It's also the science behind a maxed-out rocket car that I can ride. Plus bowling balls and an interrupting sign. Today on Science Max, Experiments at Large. Greetings, Science Maximites. I am Phil McCordick, and this is Science Max Experiments at Large. Today, we're going to be experimenting with the balloon-powered car. Here's how it works. Woohoo! It all has to do with Newton's third law.
Newton's third law. For every action, there is an equal and opposite reaction.
We don't have to do this now. This is all for later. We can build the cars first, and then we can, let's go over here. So how do you build a balloon-powered car? Well, I suggest you be science maximites, because there's any number of ways you can build a balloon-powered car. You do not have to follow my design. You should come up with one of your own. It may even be better than the one I built. But I will give you some tips, though, that make it a lot easier. First of all, you need something to stick your balloon on that has an opening on it. I used a turkey baster for this car. I just pop the top off, and remember to tell an adult that you're using the turkey baster. And then you stick the balloon on there, and it allows you to attach something to the car, and it also makes it easier to blow up the balloon. You can use any number of things, even just any kind of tube that you find lying around. It helps you attach the balloon to the car, and it helps you blow up the balloon way easier. The other thing you should think about when you make your balloon-powered car is how you're going to make the wheels roll. Once you've decided on the base of the car, you could use anything, even just a piece of cardboard like this. You can do your wheels in two ways. The first way is to attach the wheels to the axle. This is how I made the axle of this car. I used a shish kebab skewer, and I stuck it inside a straw, just like that. And then I attached the lids to the shish kebab skewer. So the lids and the shish kebab skewer are attached, and they rotate in the straw. That's one way to make the wheels turn. The other way is to tape down the axle or whatever you're going to use and have the wheels spin around on the axle. Two great ways to make your wheels turn, and it really kind of depends on the wheels you're using. You can make your own design and keep refining it and making it better and faster, or do what I like to do and make a whole bunch of different cars. So we've got this one. This one I made out of paper plates, and this is a snorkel. Awesome. This one is the rock car, because there's a rock on it. I've got the dragster model. It's a long broom handle, and it might not work that well, but who knows? And this is my favorite design. It's made out of waffles and an ice cube tray. This is why I make a whole bunch of different cars, because I can race them.
Sunday, Sunday, Sunday at the Science Maxadrome. It's the balloon-powered car winner-take-all drag race of awesome.
First up, the Eliminator.
Woohoo! Better late than never, it's the Procrastinator. Crushing the competition, it's the Terminator. Feel the chill of the refrigerator.
All right!
And last but not least, the regurgitator.
Well, when you build your balloon-powered cars, you can figure out what worked or what didn't work and try modifying your designs to make them work even better. That is science. And now we're gonna max it out, because this is Science Max Experiments at Large. So we're gonna take that small balloon-powered car that we just built, and we're gonna make it much, much bigger. I'm gonna go to the Center for Skills Development and Training, and we're gonna use the science behind the small balloon-powered car, and we're gonna make it big. That science is Newton's third law, but there's plenty of
third law. For every action,
there's
there is
plenty
an
of time for this
equal and
later. We're not doing this bit now. We're doing that bit in a minute, so we can. No, I said we're doing it later. We're doing it later. Whoa. Hi, Sarah.
Hi, Phil.
This is Sarah, and she's got a master's degree in physics from McMaster University.
That's right.
And we're going to be talking about Newton's third law. Oh, look out, duck! Sorry. There was a sign that kept coming in. Never mind. Newton's third law. Well, what is that?
For every action, there's an equal and opposite reaction.
Right, so how does that work with our balloon car?
Ah, cool. Okay, so if you blow up the balloon, what's gonna happen when you release it is the air is gonna push out with a certain force, which in turn is gonna cause the cart to move forward with the exact same force.
Yeah, works great. So how come it doesn't work with my rock cart?
Ah, wow. Well, actually, it did work. So the balloon still pushes with the exact same force, which causes the cart to have the exact same force push forward, but your rock is really heavy, so you probably didn't see it move.
Oh, so a lighter cart works better with the same amount of force.
That's it.
Well, there you go. Newton's third law. What?
Newton's third law. For every action, there is an equal and opposite reaction.
I'm really starting to dislike that sign.
Phil, are you okay?
Yeah, I'm fine.
Our small balloon-powered car works because of Newton's third law. For every action, there's an equal and opposite reaction. The air pushing out the balloon this way pushes the car with the same amount of force this way. So, in order to max it out, the plan is just to get a bigger wheeled cart and a much bigger balloon. So, everything should work out the same.
Okay, so I thought what we would do is in order to max out the balloon-powered car, what we need is a cart to start with, and then I ride it. And we have a giant balloon, and then I go.
Do you have a giant balloon?
Ha 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 ha! Giant balloon! So, step one, Sarah blows up the balloon.
Okay.
Wait. Use this air compressor, it'll probably be a lot faster.
Sarah and I get to work blowing up the balloon, and it takes a long time. A very long time.
Okay, human-sized balloon-powered car test. Take one. All right, Sarah.
You got it?
Yeah. Okay, let it go.
Okay, go.
Let it go.
I
You did let it go.
It's let go.
Nothing is happening.
It's not coming out fast enough, and you're a bit too massive. I don't think it's gonna work like this.
Really?
Yeah.
Okay. Balloon-powered car test 2. No fill. I'll just take it. What happened?
I don't think it worked. The balloon popped. Phil, are you okay?
This is why you wear protective eyewear. Yeah. So, that didn't work.
No.
No. Should we get another balloon?
I think we need something else.
Okay, well, the air coming out of the balloon just didn't have enough force, so.
We need the air to come out with more force.
Yeah, do we get, what, a bigger balloon?
I don't think that's gonna work. I don't think it's that. I think we need something with compressed air.
Oh, like a scuba tank or a...
Fire extinguisher, something like that. Yeah, that's what we need.
Okay, sure. Well, we can, all right, so I don't know if that's safe to do that, so we'd have to build like a cage or something?
Yeah, I don't know if it's gonna work on this.
All right, well, back to the drawing board. So
Okay.
what we should do is we should get
We need to find these tanks.
get the tanks, and then we make like a frame out of aluminum or something.
Okay, that could work.
Yeah,
That's a
they
good
can hold the
idea.
tanks, so
Yeah.
they're safe. And then what we should do is...
Who was Isaac Newton? He was a mathematician and probably #1 on the list of top scientists of all time. Albert Einstein said, Isaac Newton was the smartest person that ever lived. You've got to be special if Einstein is calling you smart. Newton's 3 laws of motion was a huge idea, but did you know Newton also came up with the idea of gravity? The famous story is that in 1666, Isaac Newton was sitting under an apple tree when he watched an apple fall and wondered why. Hey everyone, I just invented gravity, which was a big relief because up until then, everyone was just floating around. Okay, so it didn't happen like that. He didn't invent gravity. He gave a name to this invisible force and then described how it works. Not only did it make things fall down, but it was the same force that kept the moon circling the Earth and the Earth circling the sun. And he invented a new kind of math to explain how. We now call it calculus. See? I told you he was smart. He's very smart.
This is hydrophobic coating. Hydrophobic literally means afraid of water, but it's not actually afraid of water. The chemistry of a hydrophobic coating prevents water molecules from penetrating anything you spray it on. You can get this stuff at the hardware store, and if you want, be Science Maximites and get an adult and think of the coolest thing you could spray with hydrophobic coating. I like to use things that do not go well when you put them in water, like tissue. Yeah, doesn't look great when it gets wet. Here's a tissue coated in hydrophobic coating. Huh? Weird. Or it works the same with a paper towel. Paper towel in water, paper towel covered in hydrophobic coating, stays dry. Or how about a dinner roll? Dinner rolls really don't like water. See? Gross. But a dinner roll coated in hydrophobic coating? Weird. Just don't eat it. Now, it's time to max it out. I have coated half of my lab coat in hydrophobic coating, and the other half I have not. Hydrophobic coating, regular lab coat. Half of me is wet, and half of me is dry. What's more, half of my outfit ended up being wet and half dry because the lab coat was protecting my outfit from getting wet. Now it's time to max it out even more. We have coated my entire outfit in hydrophobic spray. My shirt, my pants, and my lab coat. The pants have been taped to rubber boots, so no water's getting in there. And my shirt has been taped to my pants, so no water's getting in there. So here's the question. Can I get into the pool and out of the pool and stay dry? Let's find out. In the pool, out of the pool, and I'm still mostly dry. Now here's what really happened. I got into the pool, and I realized I should have duct taped the pocket, because all the water went in there, down into the rubber boots, started filling up the rubber boots, and now my entire leg is full of water because the hydrophobic coating isn't letting it come out. So the hydrophobic coating isn't keeping the water out, now it's keeping the water in. Let's take a closer look at Newton's third law.
Newton's third law. For every action, there is an equal and opposite reaction.
Okay. All right, let's watch it back.
When the sign hits me, I exert a force on the sign in the opposite direction. That makes the sign stop moving. It also exerts an equal force on me, causing me to fly off in this direction.
Now, if I was to push this sign, I'm not only pushing the sign this way, but my feet are pushing against the ground in the opposite direction. It's, well, it's really easier to see if I'm not standing on the ground. No, hold on. Okay, so, huh? Oh, okay. So now that I'm hanging, watch. I push on the sign, but when I exert force on the sign to make it go this way, I go that way. Well, actually, it doesn't work as well because the sign isn't as heavy as I am. So wait, I have this over here. This is a barrel, and it has stuff in it, and it weighs as much as I do. Okay, so watch. If I push on the barrel like that, I go away from it as much as it goes away from me. So, there you have it. Newton's
third...
No, hold on. Newton's
third law.
Newton's third law. Okay, go.
Newton's third law. For every action, there is an equal and opposite reaction.
So, using a giant balloon to push me on a cart didn't work.
What happened?
The plan now is to use a compressed gas cylinder. Just like a balloon, these cylinders contain a lot of air. If we get a cart and put a gas cylinder in a cage for safety on the back and open the valve, the escaping air might have enough force to push me.
This is 2 cubic meters of air. If we were to put it in a balloon, the balloon would be this big. But if we compress the air, we can fit it all into one of these, a steel tank. This is what we're going to be using next for our air-powered car. Got it?
Yep.
All right. So Sarah and I have been hard at work, and we've built the air-powered cart. We can't call it a balloon-powered cart anymore because now we've got a compressed air tank, so it's not a balloon that powers it.
Exactly.
Okay, so I'm going to sit on here. Sarah's going to turn on the tank, and I'm going to go. And before we do this, we should say, do not, under any circumstances, try this at home. We are trained professionals. You ready?
I'm ready.
Okay, high five first. Okay, now we do it.
Okay, so before I turn the tank on, make sure your feet are down and the brakes are on.
Gotcha.
Don't take them off till I say go.
You have got it.
All right.
Ready?
Okay.
Yeah!
It worked!
Yeah, it did work, but I feel like it could work better.
You want to go faster?
I do want to go faster. This reminds me of the rock car.
Yeah.
Where we didn't have a big enough balloon.
We need more force.
We need more force. So should we get a bigger tank?
Let's get more tanks.
More?
Tanks, more force. You're gonna go faster forward, Newton's third law.
Newton's third law, high five. All right, let's do it.
All right.
Whoa. Okay. This is Newton's cradle, and it's a really cool toy that demonstrates all kinds of laws of motion, including Newton's third law. What you do is you pull this one ball out, and when it hits these balls, they exert force on that ball to make it stop moving, but it exerts force on these balls, which travels through the balls and makes this one on the end fly out, like that. Now, there's a lot going on here, but you can really see how the force is equal that you put in and you get out if you use two balls. I swing two balls up, and two balls go out that side. Isn't that cool? Now, it wouldn't be Science Max unless we maxed it out, so come on. Whoa, okay. This is one we built out of bowling balls. Bowling balls. Bowling balls. Instead of smaller balls, and I think it's gonna work the same way. Let's find out. You throw one out, and yeah, it works the same. Okay, now let's try it with two balls. Okay, ready? Wait. And two balls, throw them out. And two balls on that side. All right, so there you have it. Whoa. Newton's third law. Oh.
Newton's third law. For every action, there is an equal and opposite reaction.
So our single pressurized tank created enough force to move me, but not very fast. The plan now is to do two things. First, we're going to triple the amount of thrust by using 3 tanks. We're also going to use some pipes that lock into each other to give me an initial push. These pipes slide together, and when the air is turned on, the pressure in the pipes will cause them to slide apart, which will push me forward. After that, I use what's left in the tanks to keep going.
All right, now it's time to max it out. I've enlisted the help of a few more Science Max people. Thank you very much, Corey. You'll see now we have 3 tanks of compressed gas, and we've also got this nifty little contraption. How does this work, Sarah?
All right, so each tank is attached to a tube,
Yeah.
and you can see that each tube goes into this one main tube, so when we turn them on, pressure's gonna build up, and we're gonna go forward with more force.
Well, that's great. And Reed is stacking cinder blocks, thanks, Reed, up so that will push, the pipe will push against the cinder blocks, and then I'll go that
forward.
way. All right, well, are you guys ready?
I'm ready.
All right, let's do it. Now, again, I have to say, thank you, Corey, I've got it. This is something you definitely don't want to try at home. We are all trained professionals. We have a physics degree here. We've got TV people that make sure that this is safe. So watch it and enjoy, but please don't try any of this at home. Okay, I'm ready. Sarah, count me down.
3, 2, 1.
Yeah! Woo! Uh-oh. Woo-hoo-hoo! That was awesome!
That was really awesome.
All right, high fives, high fives. Yeah. And it's raining now, so it looks like we're gonna have to stop. So thank you very much for joining us on Science Max Experiments at Large in our episode on Newton's third law.
Science Max is a show where we take small experiments and do them big. If you want to try these experiments yourself, go to our website for instructions. But not all the experiments on Science Max are the kind you should try at home. This one, yes. This, no. Try this, don't try this. A big yes, a big no. I don't know how you could possibly do this one at home. And remember, if you're ever not sure, ask an adult. Thanks for watching Science Max Experiments at Large.
Wait, I can play Mary Had a Little Lamb.
It's working! It's working!
Newton's cradle out of bowling balls. Come on! You know this one, sing along. Whee! Come on! I mean, come on! Science! Ooh. Yay!
Have you ever done a science experiment and wondered what it'd be like if you did it big? I have. My name is Phil, and I take your everyday science experiments and do them big. This is Science Max, Experiments at Large.
Science Max! What good is science if you can't use it to give you super strength? Well, I try to do just that on this episode of Science Max. Lifting more, rolling more, and a whole lot of running. Simple machines, today on Science Max Experiments at Large. Greetings, Science Maximites. I have a question for you. Have you ever wanted superpowers? Like super strength? Well, today on Science Max Experiments at Large, I'm gonna give you and myself super strength using the power of science. But we're gonna do things a little differently today. You see, well, the portal hasn't been working perfectly since I built it. But I ordered a new particle impulse controller, and all I have to do is get it back to the lab. Perfect timing. It looks like the portal is broken. Okay, well, no problem. Okay, I'm here. Wow.
That's perfect. One particle impulse controller for you.
All right, thanks very much.
No problem.
Appreciate it.
Enjoy.
Thank you. Well, my very own particle impulse controller, okay. That's as heavy as I thought it was gonna be. All right, Science Maximites, this episode of Science Max Experiments at Large is gonna be a little different because today I'm not gonna have an expert come and help me because I'm gonna move that giant, heavy particle impulse controller all the way across the parking lot and all the way up that loading ramp by myself with nobody's help. How am I gonna move a giant, heavy machine all that way if I can barely even budget? Well, I'm gonna give myself superpowers, super strength with the power of simple machines. And the first machine we're gonna start with is the lever, which I guess I should go back to the lab to tell you about. All right, Sal, I'll see you next time. Oh, hey, how you doing? Let me guess, you got some work to do and you need it done easy, right? I mean, look at this book. I mean, you could pick it up, but what, are you gonna be some sort of book picker-upper person now? Is that all you're gonna do? Is that gonna be your life, just picking up books left, right, and center? No, you're smarter than that. You know what you need? A lever, like this. Now, I know what you're thinking. I know you're thinking, hey, this is just a plank. You're right, that's because you're smart. A plank can be a lever. All you need is two sides and a place for it to pivot. A fulcrum. It can be anything. Look at this. Bam! Now it's pivoting. I put the book on this side, and then I push down on that side. I'm doing work easy. Hey, look at me doing this work over here. If I want to do more work, I could move the fulcrum a little bit further over. Now I do lots of work, but I lift the book a lot further. Look at that. Whoa, wow, whoa, yeah. Huh? What do you say? What do you say, huh? Huh? You don't like this lever? Don't worry. Hold on, I got another one for you here. Hey, take this stick. All you need is 2 ends and a place for it to pivot, like this. Bam. Now, it's a lever. This side goes down, that side goes up. Down, up. It's a lever. It's a lever. You want to make a catapult? Use a spoon. The place where the spoon pivots is the fulcrum. And now, it's a lever. It's a lever. It's a lever. Look at this lamp. Now, it's a lever. Scissors, 2 levers. Your forearm, it's a lever, 2 ends, and the fulcrum where it pivots, yeah, the fulcrum can be at one end. Crazy. This fish, you guessed it, now it's a lever. And now you know your levers. Okay, where were we? Oh yeah, levers. So you can use levers to become much stronger, or at least lift something you couldn't normally lift. Levers are simple machines and they work like this. Levers are just a long rod or a stick or pole or a piece of wood like I've got here, and something for them to pivot on, a fulcrum. Now let's say you have something heavy, like this book. Sure, I can lift it, but what if I told you I can lift this heavy book with this book? Now, if the fulcrum is in the middle, like a seesaw, you can tell that book is much heavier than the other book. But watch what happens when I move the fulcrum. Huh? It's like magic, but it's not magic, it's science. Whoa. It's because the small weight is moving a long distance and the heavy weight is moving a short distance. Small weight, long distance, heavy weight, short distance. So, everything balances out. But here's where it gets interesting. The longer your lever, the more weight you can lift. These are 2 heavy cinder blocks. There's the fulcrum, and here is a very long lever with which I'm going to lift those cinder blocks with this book. Ha-ha! And there you have it, levers. Now, back to the particle impulse controller. Oh, right. Ha 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 ha! Lever! Here we go. I got my giant lever. The bigger the lever is, the easier it is to do the work. I need a fulcrum. Just about anything will do for a fulcrum. And put that there. Now the hardest part is getting it on the lever. Okay. All right, hardest part is over. Get the lever up on the fulcrum. And, oh, look at this. No problem, 1 finger lifting. It suddenly became very easy for me to move this. I guess I need to do more than just lift it though, huh? Because I have to move it all the way. Oh, rollers! Come on, back to the lab. Okay, rollers. Rollers are like wheels, except they're not attached to anything. In ancient times, they used to move giant, heavy blocks of stone using rollers. We can demonstrate using a book. Now get a book, put it on a table, and try to move it across the table. You'll see that it's very difficult. I can't move this book across the table. I can't. Okay, it's not really that hard, but still, it takes effort. But if we get some rollers, I like to use pencil crayons and not pencils, and here's why. Take a closer look. You see, pencils aren't round. They're hexagonal. They have 6 sides, whereas pencil crayons are round. And of course, if you want something to roll, you want something round. So get a bunch of pencil crayons and put them on the table and put the book on the pencil crayons, and you'll see that suddenly moving it is a lot easier. All right, that's rollers. Back I go. Now
it's time for Science So Simple, a Caveman Could Do It. This is a caveman. This is a rock.
Knock!
It is a well-known scientific fact that if this caveman were to try to move that rock, he would not know how to do it easily. Poor caveman. But in ancient times, people learned how to move heavy rocks using ropes
No!
and rollers.
Oh, wrong Earth.
Yes, rollers.
Wrong Earth.
Rollers.
Wrong Earth.
Close enough. Rollers make it much easier to move a heavy object. But they aren't perfect. So the wheel was invented. The wheel is a simple machine and one of mankind's greatest inventions. But no, that's not how it works.
No?
Wheels go on axles, which go under a platform. Now you have something to place that heavy rock on to move it around. But all these great inventions came after the time of the caveman. Cavemen had to do everything the hard way. Join us next time for more science.
Okay, I've got rollers. They're just plastic pipes, but they'll work perfectly. I put them here. And now to lift up the machine. Okay. Perfect. And so the rollers go underneath like that. And then whoa. Whoa, careful. Look at that. No problem. Wait, I gotta get rid of this to get it moving. Now, the trick with rollers is you have to keep taking them out of the back and putting them in the front. But, whoa, whoa, whoa. It's stop, rollers, stop. Oh no, oh no. Okay, okay, whoa, rollers, easy. There we go. Okay, in the front, roll it forward.
Now I know what you're thinking. You're thinking this seems like a lot of work. And it's true, moving the rollers back and forth does take some time. But did you know this was how the pyramids were built? It's true. Giant stone blocks were moved on rollers just like I'm doing here. And as you can see, what worked for the ancient Egyptians works for me too. Uh-oh. Yeah, there's a hill here. If I go down the hill, it's gonna start rolling faster than I can do the rollers. I'm gonna need some help. Oh, I know! Pulleys! 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 Okay, pulleys. Pulleys are a great way to change the direction of force. I've got a rope going through this pulley and down to a book. So when I pull the rope down, the book goes up. Changing the direction of force can be very helpful, but pulleys can be helpful in another way. Pulleys can let you lift something that you couldn't normally lift. Now the rope goes up and down and up and down and up and down. And the force I need to lift this cinder block is a lot less than if I was just lifting it by myself. But I've got to pull a lot more rope. That's called mechanical advantage. Spreading out the force
over a longer pull so you can lift a larger weight. If you use more pulleys, it reduces the amount of force. 1 pulley, same amount. 2 pulleys, half the force. 3 pulleys, 1/3. So I've got 5 pulleys here, which means I only need 1/5 the force to lift this cinder block. So there you go, pulleys. Now back to the, wait a minute. This calls for a mini-max. So how much weight can you lift with pulleys? Well, as much as you want, really. I have 4 pulleys on the bottom and 4 pulleys at the top. That means with 8 pulleys, I only have to lift 1/8 of my weight plus the weight of the chair I'm sitting in. And if I keep pulling, you will see that the chair I'm sitting in is roped to the pulleys. So now we see if I can pull myself up with nothing but pulleys. Look at that! I'm totally lifting myself into the air with the power of pulleys. And I don't need to use 2 hands. In fact, I only need to use 1 finger to hold myself up. And my thumb, obviously, to hold the rope. That is the power of pulleys. I can almost make myself fly. Well, almost. Now, back to the particle impulse controller. Letting myself down. Whoop. Whoop, whoop, whoop. Particle impulse controller. Let's go. Wait. All right, I've been able to use this pulley to lower it down the hill at the speed I want to go. Interestingly, I'm using the pulley not to make it lighter, but to just change the direction of force. And I managed to get it right here at the bottom. Now I've got to get it up onto the loading dock, so I think this is where I need a ramp. Whoa, whoa, oh. Here is something mind-bending you can do with pulleys. These buckets are attached to the table through a pulley. There's nothing holding this table up except for the weight of the buckets pushing down on the table. So if I took the buckets off the table, the weight of the buckets pulls the table up. But because the buckets are on the table, everything is in balance. Mind-bending, right? Okay, wait, it gets better. If I took a weight and I put it on the table, the weight of the buckets isn't enough to keep the table up. So I have to add more weight to the buckets so the buckets pull the table up. Whoa. And there you have it. It's weird, it's mind-bending, it's science. Okay. Ramps. Ramps are a great way to move something up. I will demonstrate using, you guessed it, a book. Let's say I wanted to move this heavy book on top of this stack of books using just this little string. Watch what happens. The string breaks, but if I built a ramp to get the book on top of this stack, and I use the same kind of string, watch what happens this time. Whoa. You see, the ramp distributes the force, so you use less force to pull the book over the same amount of distance, and I can get it up to the top of the stack of books, and the string doesn't break. So ramps. Let's put them into action. Woo. My simple machines have worked great. I've managed to get the particle impulse controller all the way to the loading dock. But now it's time for the hardest job. What I need to do is build a ramp that goes from the ground up to the loading dock. Then I need to pull the heavy impulse controller up the ramp. The best way to do that is to use a system of pulleys. I have 3 pulleys on one end and 2 pulleys on the controller. Because I have 5 pulleys working together, I'll only have to lift 1/5 of the weight. The plan is to get it tipped over onto the ramp, then use rollers to help it roll up as I pull on the rope. There's 3 pulleys on that piece of wood over there, and I got 2 pulleys on this piece of wood here. And now, if I pull, and I carefully put the rollers underneath, careful, careful. Perfect! Okay, now it's on the rollers, and now I can pull it up the ramp. Now, I gotta carefully put new rollers underneath as I go. Pull it up the ramp. Roller. I know what you're thinking. It still seems pretty difficult. If only the simple machines could give me longer arms. Well, they can't do that. But what they can do is give me the strength to do this heavy job with no one else around but me. Hopefully that won't be a problem. There we go! I did it! All the way across the parking lot and up onto the loading dock with the help of levers, rollers, ramps, and pulleys. The hard part's done. Now I just have to get it into the lab. All right, let's see if all that effort was worth it. I think it's working! Well, there you go. Thanks very much for joining me on Science Max Experiments at Large. I think I'm gonna go home because it's been a long day and I could really use the rest. See you next time. Wait, I hit 3, 4, 1, 2. I should have hit 3, 4, 2, 1. Yeah, that's okay. I'll just go back and, Now, this is a lever. See, it's a catapult and a spoon. It's 2 things in one. I mean, it could also be, it could also be some sort of, like, it's like an eye patch. Have you ever done a science experiment and wondered what it'd be like if you did it big? I have. Yeah! My name is Phil, and I take your everyday science experiments and do them big. This is Science Max, Experiments at Large. Science Max! This episode of Science Max is all about liquids. What makes something float or not float?
Oh no! My loonies!
Liquid density and super absorbent gel.
Who wants to do an experiment with diapers?
Liquids. Today on Science Max, Experiments at Large. Hey, welcome to Science Max, Experiments at Large. I'm Phil McCordick, and hold on a second, I'm just gonna change. Okay, that's better. Now, where were we? All right, let's go make a boat. So you know that some things float and some things sink, like rocks, or wood, or full water bottles and empty water bottles, or carrots, foam, waffles, screwdriver, playing cards, plasticine, tinfoil, potato, my watch. Wait. That wasn't supposed to go in there. So how do you make a boat? You make it out of something that floats, right? Well, most boats are actually made out of metal. Tinfoil is metal and, well, it sinks. But if you fold tinfoil into a boat shape, it floats. And boats don't only float themselves, but they can hold people and cargo. In fact, there's container ships crossing the ocean at this very moment that are holding thousands of tons of cargo, and they're all made of metal, which doesn't float, it sinks. So how do boats do it? Are they magic? No, of course not. Boats are science. And here, you can be science maximites. Get some tinfoil and cut it into the same size pieces and fold a couple different shapes of boats and see which one can hold the most weight before sinking. And now it's time to max it out.
But before we do, here's how you can fold your own tinfoil boat in less than 15 seconds. First, take a square piece of tinfoil, then fold it in half. Fold one corner down and the other corner down. Then open it up and ta-da, you're done. If you want instructions on how to fold a more complicated boat, go to our website.
I have a feeling I'm gonna need a few extra lab coats for this experiment. Like I was saying, let's max out the tinfoil boat and find out a little bit more about why boats float. Okay, well, I'm here at an indoor pool, which is not, I wasn't expecting to be in the pool just yet, but this is where we're gonna build our giant tinfoil boat, so why not? Huznia.
Phil, you're wet.
I thought I was gonna come in over there, but I came in on the water sled. I think I had the coordinates wrong. Anyway, this is Huznia, and she's from Let's Talk Science, which is all about science education, right?
Yes.
Just like us. So you're gonna help me max out the tinfoil boat. I think I dropped it in the water. Hold on. Whoa! Here, where? There it is. The tinfoil boat. The tinfoil boat.
Phil, this is a boat?
Well, it looked a lot better before I came down the water slide, but that's the idea, and then we make it bigger. What do you think?
I don't think it's gonna work.
Oh, well, why not?
Tinfoil is very thin,
Uh-huh.
and it might not hold the shape of the boat.
Well, I still think we should use tinfoil, though.
Why?
Well, because the small experiment was tinfoil, and I bought all of this tinfoil.
Then let's do it.
Tinfoil? Okay, high five. I'll take the tinfoil, and you take that, and I'm gonna have to dry off at some point.
Welcome to Shipbuilding for Pirates. I'm Swubby, and I've built some of the finest pirate ships for some of the finest pirates this side of the Caribbean. And I can teach you to do the same. But first, you need to know your basics. Mass and volume. Let's start with volume! But not that kind of volume. Which of these two chests do you think has more volume? Right, this one here. Which of these two balloons do you think has more volume? Right, this one here. Volume is how much space something takes up. Which of these two chests has more volume? That's right, they're the same. But which of these two chests has more mass? Which is heavier? Hard to tell, isn't it? But what if I told you that this one was empty and this one was full of treasure? Oh, loonies. Now, which one has more mass? That's right, this one. These two chests have the same volume, but this one has more mass. This chest has more volume than that one, but this one... My loonies! that chest does not have as much mass. Volume is how much space something takes up, and mass is how heavy something is. And when you look at them both together, you're looking at density. Join us next time on Shipbuilding for Pirates, and then we'll look at how volume, mass, and density work together to make something float. Oh, my precious, precious loonies. Are you all right, my pretties? They can't talk, so I'm not sure what they're saying.
So, Husni and I get to work constructing a large tinfoil boat. Our first design is just sort of a square, folded together out of a very large sheet of tinfoil. Simple, but can I ride in it? There we go. A giant tinfoil boat, just my size. Woo-hoo-hoo-hoo!
I don't know if it's gonna work. It's too thin.
You think it's too thin?
I feel like yes.
What should we do?
Do you want to test it?
Let's test it. Okay, good idea. So here's the most important question. Do you want to test it or should I test it?
No, you test it.
All right, here we go. Putting it in. First test, does it float on its own? Yeah! Floats on its own, no problem. If I just get in very carefully, then it will work fine. See, if I'm careful about how I get in, no, it's fine. See, if I just get in like that.
Bill, are you okay?
Wait a minute. It's sort of, no, that's just air. You know what went wrong? It wasn't boat shaped. I think if we make it look more like a canoe, because canoes float, if we make it look like a canoe, it'll work great.
No, Phil. We need some support. If we add a couple of structures in between, then we add support to it.
I'll tell you what, let's make a boat like I want to make and a boat like you want to make, and we'll see whose is the best.
That's a good idea. Okay, let's do that.
All right, let's do it.
Welcome back to Shipbuilding for Pirates. I'm Swabby, and now we know what volume means, what mass means, and that together it can tell you something's density. Now let's find out why things float. Let's say we're out to sea and my treasure chest gets swept overboard. Oh no! But it's all right. It floats because it pushes enough water out of the way, displaces it to carry its mass. But what if my treasure chest had more treasure in it? Well, we're giving it more mass, but not more volume. Too much mass and not enough volume, and it will sink. Oh no, my loonies! You need more volume if you want to float more mass. And that is why things float. I'm Swabby, and thanks for joining me on Shipbuilding for Pirates.
So, the first version of the tinfoil boat didn't work out too well.
Like that.
But my idea is to build a tinfoil boat more like a canoe to see if a different shape makes any difference. Tinfoil canoe!
Very Canadian.
Very Canadian. The canoe part, anyway. I don't know about the tinfoil part. So, Husni and I had a bit of a disagreement of why the last boat didn't work. I thought it was because it wasn't shaped enough like a boat, so this one looks like a canoe.
What I thought is that it requires some structure.
Structure so that it wouldn't fold together.
That's right.
And we'll see how it goes.
All right.
All right, here we go. Did it work?
No.
Okay, your idea next. Did you know it's easier to float in salt water, like in the ocean, than it is in fresh water, like a lake or a pool? That's because not all liquids are created equal. They have different densities. This is fresh water, or it doesn't have anything in it. And this is sugar. If I was to put 1 scoop of sugar in this water and stir it around until it dissolves, now this liquid is more dense than before I put the sugar in. Here's an experiment you can do at home using liquid density. This glass just has regular water with yellow food coloring in it. This glass, green food coloring and half a cup of sugar in it. This one has a full cup of sugar in it, and this one has 2 cups of sugar in it. Now, when you do this at home, you'll definitely want an adult to help you because you have to heat the water if you want to dissolve that much sugar in 1 glass of water. I'm gonna put them all in 1 container. You can do this at home, and when you do, I suggest you use a very small container because you have to be very careful when you put the layers in. You can use a turkey baster or a straw. When you put your finger on top, the air pressure will hold the liquid in and you can just drop it in. But these kind of take some time, so I'm going to use the syringe of science. I'm gonna use the most dense liquid first because that's the one that's gonna want to be on the bottom. I carefully put it on the bottom of the container. The next layer, be very careful. And you'll see that the red and the blue aren't mixing because they have different densities. The blue is heavier than the red. We'll add the green, and you can see even when it drips into the red, it comes back up to the top because the green liquid isn't as dense as the red liquid, and the denser liquids push the lighter liquid up. And now we're gonna add the yellow, which of course has no sugar in it at all. And there you go. All the layers stay separate. If you put it on a light, you can really see it. Liquid densities. Now, let's max it out. Ta-da! The longest length of liquid layers. 12 liquids all organized by density. Starting from the bottom, we have honey, corn syrup, chocolate syrup, maple syrup, dish soap, whole milk, water, dyed blue, vegetable oil, extra virgin olive oil, rubbing alcohol, baby oil, and lamp oil. Liquid density. I really want to mix it up, but it took me a long time to make this, so I'm not going to. Our first 2 attempts at a tinfoil boat haven't gone so well. Husnia's idea is to make a tinfoil boat and add some more structure, because the tinfoil just wants to collapse when I get in it. So we start with a large piece of cardboard on the bottom, then we wrap the tinfoil around it and shape it into a boat. After that, we add some supports across the top to stop it from folding in when we add my weight to it. This boat feels a lot stronger than the one I was just in.
I told you.
So how does all of this work?
So we got some support using broomsticks and then some cardboard paper. And then underneath we have cardboard.
And so how will all of this help the boat not sink with me in it?
Right. The broomsticks will prevent it from folding this way and you won't sink.
Good.
The cardboard will prevent it from folding this way and you won't sink again.
Not sinking is my favorite thing to do in the tinfoil boat. All right, so let's try it.
Let's do
now,
it.
Are you gonna get in this one?
I'll tell you what, Phil. If you get in and you don't sink, I'll go after you.
Deal.
All right.
All right, here we go. It's sort of working. Oh no, water's coming in. It's sort of working.
It's almost working.
Uh-oh.
Wow.
No.
Hold on.
1, 2, 3, go. Another thing I learned is that a very light tinfoil boat can be very heavy when it's full of water. I don't know if fixing it is in the cards. I think we're gonna have to build another boat. So what do you think we should do?
Let's add more structure.
More structure?
Oh, yeah.
What if we add like a metal rod around the outside and maybe some more metal rods and ribs? And we wrap it all in tinfoil, and you think it'll work?
Let's give it a try.
Let's give it a try.
Don't worry about it. I got this.
No, I get it. I'll get it.
Sure?
Okay. Who wants to do an experiment with diapers? Oh! No, I'm serious. You may have a little brother or sister at home, which means you probably know where you can find some diapers. But there are 2 things you need to remember. First, ask an adult if you can use the diapers for your experiment. And 2, only use unused diapers. Okay? Okay. So, you take the diaper, And if you cut it, be very careful, maybe get an adult to help you, over some black construction paper, like I have here, and you shake the diaper over the construction paper, you'll see that there's a little powder that comes out. And this is the secret ingredient. This is super absorbent gel. What it does is it soaks up all the liquid, and diapers are full of them. And you carefully pour it into a plastic cup, like that. Now you can see I have already done it with a number of diapers. It's important to use a plastic cup because it's a little messy, although it's non-toxic, it's totally safe, but it's still easier to clean up by just throwing the cup away. Now, add some water, and what happens is this super absorbent gel absorbs the water and turns very quickly into a paste. Look at that. Now, let's max it out. 5 kilograms of super absorbent gel, 500 liters of water. Now, it is time to do science! And I have my own stir stick. Yep, definitely coming along. I'm not exactly sure if we're getting anything on this camera, but I want to make sure it's recording. Yep, it's recording. There we go. It is definitely turning solid. Well, there you go. The giant super absorbent gel experiment. Corey, Trevor, I need some help getting out. How many outfits have I been through in this episode? How many outfits have I been through in this episode? Anybody have a towel? There you go. Thanks, buddy. That's great.
Husnia's idea of adding structure to the tinfoil boat was definitely right. We just needed to go further. So we did it again. This time, we made a much larger boat. We started with a sheet of cardboard, then wrapped the tinfoil around and added some metal supports taped to the cardboard across the boat this way to make ribs, as well as some other supporting pieces in the front and the back. Then another metal rod all the way around the top, and finally, supports across the middle.
All right, feel how strong it is. I'm really excited about this version of the tinfoil boat. What we did is we used thwarts, big hard pieces of wood that we did last time, but this time we have ribs.
Ribs, right, which are made of a cardboard, a metal rod attached to it,
and shaped, and we did a whole bunch of them that go the whole length of the boat. And then we used all of this bendable metal, and we have one that runs all the way around the gunnels, and a whole bunch that run down the inside, and we even used bike fenders at the front and the back of the boat to give it super rigidity so that it hopefully won't go like all the other boats have done so far. Are you ready, Husnia?
Let's do this.
1, 2, 3, lift. All right, let me get over. It floats, but that doesn't tell us anything because they've all floated at this point. It's only when I get into it. Okay, here we go. All right. Hey! Hey, it works! All right.
Oh, it's working.
Ha 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 ha! Look at that! It works perfectly. The tinfoil boat experiment has been done. Science Max, experiments at large. What do you think, Husnia?
The only reason I got into this boat because I knew it's gonna work.
Really?
Oh, yeah.
So you knew you would never get wet? See, I don't think that's fair. I think it's time that you got wet. Yeah, I think we should go. I think you and I should just get wet right now. Just need
someone help.
You're still dry, aren't you? That is so unfair.
Science Max is a show where we take small experiments and do them big. If you want to try these experiments yourself, go to our website for instructions.
But not all the experiments on Science Max are the kind you should try at home. This one, yes. This, no. Try this, don't try this. A big yes, a big no. I don't know how you could possibly do this one at home. And remember, if you're ever not sure, ask an adult. Thanks for watching Science Max Experiments at Large.
Science! I don't know what you're saying. I don't speak treasure chest.
The one thing I'm really trying not to think about is that this is the stuff that's in diapers.
Let me talk to your brother. Whoa, 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 whoa. Don't talk with your mouth full.
Have you ever done a science experiment and wondered what it'd be like if you did it big? I have. My name is Phil, and I take your everyday science experiments and do them big. This is Science Max Experiments at Large. Science Max! This episode of Science Max is all about elastic energy. We use it to build a catapult and a paddle wheel boat, and then we max them out. We even learned some history. Elastic energy. Today on Science Max Experiments at Large. Welcome to Science Max Experiments at Large. I'm Phil McCordick, and today we're going to be building one of the most devastating, one of the most powerful machines known to medieval man, using a plastic spoon, among other things. We're going to be building a catapult. Catapults were used throughout history for all kinds of reasons, to throw all kinds of things, but mostly big stone blocks at castle walls in order to knock them down. Here's what you need in order to build your own catapult. You need elastics, pencils, unsharpened is fine, plastic spoons, like I said, and popsicle sticks. Popsicle sticks. Popsicle sticks. I'm gonna go wash my hand. So, here's the science behind what we're doing today. It's all about elastic force. Elasticity is a property of solid materials, like this elastic, and how much they tend to return to their original shape when deformed, like when I pull on it. Elastics are called elastics because they're great at doing just that. You can pull on it and pull on it and pull on it, and it'll, always return to its original shape. So we are using the power of elastic force today. Ow.
Now it's time for a Science Max quiz. Elasticity is the ability for a material to return to its original shape when deformed, like this or this. Which of these materials have elasticity? A rubber band, a pencil, or a rock? Haha! This is a trick question. The answer is all three. Most solid materials have elasticity. Nearly everything will deform a little and still be able to return to its original shape. It all depends on how much. This is a steel bar. This is an elastic band. And this is an ice cream sundae. We're not talking about ice cream sundaes now, though. So get that out of here. Good. Now, a steel bar and an elastic band both have elasticity. A steel bar can be stretched to 1% of its length and still spring back. A rubber band can be stretched 300% or more. The difference between the two is why we make balls out of rubber and buildings out of steel, because the other way around wouldn't be good for balls or buildings. This has been a Science Max quiz.
All right, let's build our catapult. The first step, take 4 pencils and stick your popsicle stick in between so you have 2 on the top and 2 on the bottom. And then use your elastic to go around and around and around. That's why I like building things with elastics, because it makes it very fast to tie things together, because once you go around and you have it nice and tight, you just pop it over the end and voila, it stays together. And that is how you start making your frame. Put more pencils on that side.
And another popsicle stick on the other end, held on at the corners with more elastics. Then, take even more elastics and put them right around the middle until you get
this. I've added a few more elastics around the middle here, and that is where we're gonna get all of our elastic force. I think I have 6. The more you use, the better it's going to work. Take your popsicle stick, stick it in between the elastics, and then start spinning it around. Here's the reason I use pencils and popsicle sticks is because the pencils are a little bit longer, which allows you to twist the popsicle stick around in the middle and build up the elastic force. Now, because I'm twisting, the elastic force we're using here is called torsion, or twisting force. When you feel you have enough torsion, pull your popsicle stick down a little bit so it won't unwind on you, and you'll see that you have all kinds of elastic energy. Then, take your spoon and stick it on the popsicle stick, and you can also break off the popsicle stick if you want to make sure it's the right length. And it works like that.
To make the frame, you just need more pencils and elastics. The trick is to make a triangle with 2 pencils attached to your frame. They should stick up right where your catapult arm would be fully upright. Then, take a final pencil and put it across the top. Don't forget to pull the arm back before you put the pencil across, otherwise it'll end up on the wrong side.
Now, this is very complicated, and I went pretty fast, so if you want the step-by-step instructions on exactly how to build this, go to our website. And there you go, a catapult of your very own that you can use to knock down very small castle walls. I've also built a larger catapult using all of the same principles. Pretty good, huh? It's got a longer arm, which means I can throw marshmallows even further. Whoa. Or I can throw larger marshmallows, or I can throw very large marshmallows. Now I know what you're thinking. You're thinking, Phil, is that the largest catapult you're gonna make? Well, of course not. This is Science Max, experiments at large. I'm headed to the Center for Skills Development and Training, and we're gonna max out the catapult so that it's big enough to throw one of these. Hey, Zach.
Hey, Phil.
How you doing?
All right.
This is Zach. He's a mechanical engineer, and you build machines for a living, right?
That's right.
Great, because I need help building a catapult.
Okay, but what's with the pumpkin?
Well, the pumpkin is what I want to throw out of the catapult. See, I figure we just take the small design and we just make it so that we can throw one of these. What do you think?
You're gonna need a really big catapult.
Yeah, and I'm also gonna need some really big elastics. Where do you get those?
Well, in medieval times, they used rope to make large catapults.
Oh, okay, well, rope is a lot easier to get, and that would be fine. And I want to make this arm as long as this piece of wood here.
This is gonna be a huge catapult.
It's a huge catapult. I guess we should build it outside, though, huh?
Let's do it.
Okay, it's over that way.
Okay.
I'll follow you.
Sure, do you want a hand with that?
No, I'm fine. You go ahead, and
Okay.
I'll just, maybe if you hold the door open for me, I could just hold, no, you know what, you go and I'll meet you.
You sure you're good?
Our full-size catapult is going to look a lot like the popsicle stick version. We start with a 4-sided frame and add some legs on the bottom. Our spoon is going to be replaced by a long throwing arm with a basket on the end. Then we need a really strong cross brace at the top to stop the arm. Just like in the small version, using a triangle shape is the best because triangles are very strong. Finally, we need something to wind around and around, which is going to give us our elastic force. Instead of elastics, we're going to be using rope for our catapult because rope has just the right amount of elasticity. But unlike medieval times, we're going to be catapulting pumpkins. Once Zach and I got it all put together, it looked like this.
Okay, we have built a catapult. Check it out. It's pretty solid, and I think it's pretty amazing. And just like in the small catapult, we have our elastic force. but this time we're using rope, right, Zach?
Yes.
Okay, and rope will work as well as the elastic did in the small one?
Yeah.
All right, great. So what do we do? It's really loose now.
We need to wind this up so that we put some tension into it.
Go!
The reason a catapult works is because the rope is twisted. The elasticity in the rope wants to unwind, which gives the catapult its power. Just like the small catapult, the more you wind it, the better it works.
Good. Usually in medieval days, they had whole teams of people doing this job, but it's just me and Zach now. How you doing, Zach?
All right.
Okay. And then we clamp it on here. So the thing doesn't unwind, right?
Yeah.
Good. All right, now we have our pumpkin, and we're gonna fire our pumpkin in our castle wall, which is made out of cardboard boxes over there. Pumpkin. All right, here we go. Pulling the arm back. Oh, that elastic force is pretty strong. Okay. How do you think you think that pumpkin's a good size?
Oh, it's pretty big.
You think?
Oh, a little too big.
It's too big for our basket.
Yep.
Smaller pumpkin! Smaller pumpkin! I'll hold this. No rush, Zach. No rush. Okay, rush, Zach. Can't hold.
Oh, yeah.
Can't hold arm. Okay, ready? 1, 2, 3! It didn't work that well.
No, not quite that well.
Yeah, so
Let's see.
it went, and it flew, and it landed here, which is a little farther away from the wall than I'd like it to be. 1/3 of the way to the wall! I don't know if that's enough. What do we do to make it better?
Well, the way we're throwing it right now, we just have the pumpkin in a, at the end of the arm. But if we make some kind of a sling so that we fling it as we're bringing it up.
We make a sling?
Yes.
All right, I don't know how to make a sling, but you know how?
Sure.
All right, we'll make it, and then you can explain how it works.
Yeah.
All right, good. Let's put the pumpkin over here. We'll recycle it later.
Max Historica.
Good morrow to you. I am Lord Fillington III, and welcome to my medieval castle. Throughout history, lords and kings have built castles and walls to keep people out. I built my castle to protect my prize collection of snow globes. I have so very many, and they're all mine. Ha ha! Oh, hello! You down there! You can't come in. This is my castle.
And throughout history, there have been people who've been wanting to get into those castles because Lord Fillington has been hogging all the snow globes, and I'd like to look at them. But the hard part is figuring out how to get into the castle, because I can't just come up to the wall and start hammering on it. Huh?
Taste the wrath of my water balloon!
Because if I get too close to the castle, he can get me. Ha 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 ha!
Fortunately, there's this thing called a catapult.
Oh, fiddlesticks. They have a catapult.
What you do is you put something heavy in the end here, and the catapult fires it at the walls of the castle, knocks them down, all from far enough away that the people in the castle can't get to you. Ah! Oh, I surrender! Don't knock my walls down! It'll take me all week to fix them. Oh. All right, you can have a snow globe. Oh. And that's how catapults were used in history. Oh, so beautiful.
Back to our maxed out catapult. Our first design threw a pumpkin just like it was supposed to, except it only threw it 1/3 of the way to the wall. Now Zach and I are planning to outfit the catapult with a sling. The sling attaches to the end of the throwing arm and gives the pumpkin a lot more distance to travel. Because the pumpkin is traveling a longer distance in the same amount of time, it will be going faster, which will hopefully get it to the wall, or at least a lot farther than before.
So we built this sling. How does this work, Zach?
Well, we've got one end tied here.
Yeah.
And then we put the pumpkin in here.
Wait. Okay, pulling arm down. Pulling arm down. Okay, yeah, now what?
Now we put the pumpkin in here.
Put the pumpkin in there.
Yeah. And then we loop this over the back of the... Over that. As the throwing arm goes up, this will slide off the back of the throwing arm and it will release the pumpkin.
All right, you're the expert. I believe you. Let's try it out. 3, 2, 1. Whoa! Okay. That works really well. You know what the problem is, though? We still don't have enough oomph.
Yeah, it needs more power.
So what do we do? I don't know if we can crank that rope anymore.
I think we're at the limit of our rope power, but if we added some more elastic...
I thought we weren't going to use elastic.
Well, we used elastics in our small demo model, so what if we use some more?
We have elastics? I don't know
yeah,
if
I brought some in here just in case.
What's this?
It's surgical tubing.
It's like a giant elastic. Well, I guess this is elastic force, so do we twist it around at the bottom there?
Well, we just wrap it around the throwing arm like this.
Oh, I see. So we tie it here.
Yeah, we just need a lot more, and then
we pull this, and it would be. Oh, yeah, that would make a lot more. So we just need a lot more of this elastic. What is this again?
Surgical tubing.
Surgical tubing. It's like a giant elastic. Fantastic. All right.
Goggles on.
Goggles on. Yes. Yes. Here's another fun way you can play with elastic force. Take a milk carton. I prefer Science Max milk because it's the creamiest. 2% cream, 100% science. Wrap some elastic bands around it with some popsicle sticks on the bottom, sort of like feet. Then take some clamshell packaging, which wraps just about anything you buy nowadays, and cut out a square or a rectangle. Then wrap some tape around that square with an elastic in it, and put the elastic on the feet of your milk carton. Then wind it around and make sure you go backwards so your paddle wheel boat will go forwards when you put it in the water. And there you go, a paddle wheel boat. Now it is time to max it up. Ahoy, the SS maxed out elastic force paddle wheel boat mattress. I need a better name. But I've made a giant paddle wheel boat that will work on elastic force because I've got surgical tubing as my elastics, and that's an air mattress. And then I use some lumber to hold it all together. And of course I need a paddle wheel, and what better thing to use in a pool than a flutterboard. Okay, here we go. So normally you're not allowed to wear your clothes and your shoes in the pool, but I got special permission because of science. Besides, I'm not worried at all, so I didn't wear my swimming outfit because I figure I can totally do this entire experiment without even getting wet. That is how confident I am. All right, now the tricky part, we'll be getting onto the mattress. Okay, here we go. Ha-ha! Whoa. Ha-ha! The SS Science! Hey, SS Science, that's a great name for this. Look, it works great, and I managed to stay totally dry. Huh? Well, almost. Whoa, oh, oh. Haha, you thought I was gonna fall in the pool, but I didn't. Uh-oh. My flutterboard has stopped moving, and I'm in the middle of the pool. Almost. Yeah. Didn't think this through. No. 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 No, that's not going to work. Maybe I'll wait. Our maxed out catapult was working well with the sling we attached to it, but it still didn't make it all the way to the wall. Zach's idea is to attach a bunch of surgical tubing to the cross piece of the catapult. Surgical tubing is pretty much big elastics, so we'll have two places we're getting elastic force from, the rope and the surgical tubing. Hopefully this design is enough to help our catapult fling a pumpkin far enough to hit the castle wall. All right, here we go. You hold that. I get this. We got our system down now. Okay. This goes up to there. Okay. Okay.
3, 2, 1. Nope. 1, 2, 3. Oh! It went too far. It went too far. That's so good. Oh man. Okay, so all we gotta do is move the catapult back. So you get that side, I'll get this side, and we'll move the catapult. See, now our catapult is too good. We gotta back it away from the castle. All right, let's go again. Aha, pumpkin.
Pumpkin.
Pulling arm back.
Pulling arm back. Grunting.
Loading. Pumpkin. Hooking rope on arm.
Hooking rope on arm. More grunting.
More grunting. Pulling back strongly. 1, 2, 3. Oh. Oh. Oh, wow. Woo.
We're inside the castle.
We're still inside the castle. Oh, man. It's an excellent shot, though. So what do we do? Move the catapult back?
Yeah.
Move the catapult back. What about
here?
Here. Here we go again. Pumpkin.
Pumpkin.
Loading arm.
Loading arm.
All right, you ready? You think it's gonna work? We've done every modification we can possibly do. So you think it's gonna work this time?
We did it. It's gonna work.
Okay, here we go. I'm excited. All right, ready?
Ready.
1, 2, 3. Whoa! Yeah! Woohoo! High fives! Well, there you have it. Awesome job. Now we need to throw fingers to see who gets to rebuild the castle. Okay? 1, 2, 3. Oh, thanks very much for joining us. Let's take a break. I'll rebuild the castle. You see, this is exactly how catapults used to work. They'd hit the same part of the wall over and over until they made a big hole, and that would weaken the wall. Fortunately for me, it's really easy to fix. Just put this right in here. Oh, man. The pool will be closing in 5 minutes.
No, I'll do it. No, I'll wipe the last.
Taste the wrath of my water balloon!
I don't believe it really sells it if he doesn't smash the water balloon. Does he? Good moral to you! I got my feather in my face.
Oh, you gotta be kidding me!
Have you ever done a science experiment and wondered what it'd be like if you did it big? I have.
Yeah!
My name is Phil, and I take your everyday science experiments and do them big. This is Science Max, experiments at large.
Science Max!
3,
2,
1.
We're really under pressure during this episode of Science Max. Compressing a gas till it's pressurized is how we can do this, and to a lesser degree, this.
Help, I'm being crushed by all this pressure!
Pressure, today on Science Max, experiments at large.
Phil to Mission Control. Come in, Mission Control. This is Mission Control, Phil. We read you loud and clear.
Greetings, Science Maximites! Welcome to Science Max Experiments at Large. My name is Phil McCordick, and today we're gonna be building an air-powered rocket. Too difficult, you say? Nonsense, it's easy. It's not like it's rocket science. Hey, it is rocket science. Cool! Here's what you need. You need a bottle and a cork. Make sure that the cork fits nicely into the bottle, and then you need an air pump, because you can't have an air-powered rocket without air. And on this air pump, you need a pin, the special kind that you use to inflate basketballs or volleyballs or stuff like that. Now, what you want to do is push the pin through the cork. You might want an adult's help for this. Push it through until it goes through on the other side,
and then make sure you get a good seal with the bottle. Now you're ready to launch your rocket with air pressure. But first, let's do a few other things. Take your cork and put it in a tripod launcher. You can make this out of pencils or anything you want, as long as it stands up nice and solidly. And then, of course, you want to decorate your bottle so it looks like a rocket. This is my rocket. Pretty good, right? So stick the bottle on the cork like before, like that. And then you stick the pin in the bottom. And what we're gonna do is we're gonna inflate the bottle with air pressure, and then it's gonna launch. Okay, here we go. You know, rocketry really isn't something you should do indoors. Come on.
This was supposed to be a field. What's going? Why are there? Oh, it's in my shoe.
Oh, this will do nicely. Now, don't forget to do this with an adult, and don't forget your safety glasses. Now set up the rocket in a nice big open area and make sure it's pointed away from you. And then what you do is you pump the air pump. And it puts air into the rocket, which pushes down on the water, which will push down on the cork, until eventually... So, be Science Maximites and come up with your own rocket design. Try different amounts of water, different fins, even a different sized bottle. Try it for yourself and see if you can get one that goes higher than mine just did. How did I get in? I think it was this way.
Do you want step-by-step directions on how to build your own air-powered rocket? Well, don't worry. Everything you need is on our website.
All right, now it is time to max out our air-powered rocket. I've got Adam here. Hey, Adam.
Hey, Phil.
How you doing?
Good, how are you?
Good. Adam's from Logix Academy, and you guys go into schools and talk about science.
We do.
Fantastic. Do you guys do a air-powered rocket?
Yes, exactly.
Does it look like this one?
Looks exactly like that.
Oh, that's great. So how do we max this out?
So we want to add more pressure to this bottle to try to get it to launch a little bit higher.
More air.
More air.
Great, so what do we do?
So we're gonna use one of these.
Ooh.
It's an air compressor.
Right, which works a lot like the bike pump, right?
Yeah, exactly.
Cool.
So we're gonna have compressed air coming from here through this tube into underneath here, and out that nozzle there, and you're going to put your bottle on top.
And out the nozzle
Just like
into
that.
the bottle, like that.
Yep, and now we want to be able to hold it in place, so we're gonna have these little fingers here that are actually gonna work to hold it until we want to let it go. So we're gonna lock it in place.
Oh yeah, look at that. Totally locked.
Exactly.
And then what? How do we launch
Now,
it?
you're gonna take this cord and go a safe distance away, and we are going to pull it.
And then we would pull it. Which one do you want to start with?
I think we should use